Bismillahirrahmanirrahim. Ladies and gentlemen, welcome to PISTAR online workshop number 22, 22nd ever since June of 2020, subsequent to the advent of COVID-19. So we have been doing it on a once a month basis, and I'm so delighted to share with you that today it is the 22nd. And it is the third workshop by Dr. Pedro Campos on data mining. So welcome everybody. And Thomas from Kenya has also joined, Dr. Thomas. Now I'm wanting to share my screen. And please let me know if you can see my screen. Yes, you can?
Yes,
okay.
You can see it.
All right. So I will try to quickly do the slideshow, and if it gets stuck, then you know I have to get out of it. But let me try. Okay, so this is workshop number 3, and this is our vision statement, and this is our mission. And my name is Saleha, and the General Secretary of PISTAR and the focal person for the PISTAR International Training Program through online workshops is Dr. Syed Wasim Abbas. And this is the PISTAR team: Mr. Muhammad Iftikhar, Dr. Sharka Hashmi, Professor Muhammad Aslam, Mr. Muhammad Jawad, Ms. Lekha Mashkoor, Dr. Haris Khurram, Ms. Kamal Aslam, and Ms. Aqsa Abid. These are the names of the international participants, and these are the national participants. And the plan for today, this time it will be even more brief than last time, because now almost everybody knows Pedro, but a brief introduction and then a presentation by Dr. Pedro on data mining, along with demonstration on software. And then after the break, which is at 4:20, according to the Asr prayer time in Lahore, we will have a 10-minute break then. And after that, I will be announcing one more time regarding the upcoming virtual conference and post-conference workshop. And after that, further presentation by Dr. Pedro. And then we can have about 10 minutes for Q&A. Please do indicate in the chat if you do have some questions which you want to put at the end. Otherwise, Pedro is very open to questions even during his workshop. And then at 5:15, we can, today, because it's the last workshop, I really want some of you to jot down some points, what you learned, what you would still want to learn, maybe in some other series, and whatever, but we do need feedback. Please, ladies and gentlemen, open either your pen and paper or your Word file where you will jot down what you want to say. And then words of appreciation by Dr. Haris Khurram, who's a core team member of PISTAR, and then the closing remarks. So now I proceed to a very, very brief introduction of Dr. Pedro. He's assistant professor at the University of Porto, the Faculty of Economics, and he teaches statistics and computer science. And he is also deputy director of the International Statistical Literacy Project. He's a researcher at LIAAD, the Laboratory of Artificial Intelligence and Decision Support, of INESC TEC, where he coordinates the research line of agent-based modeling, which intrigues me, as I've already shared with you. His current research interests: data science, network mining, artificial intelligence, multi-agent or multi-agent systems, statistical education. I know him from statistical education, from the numerous conferences that I have met him in all so many different parts of the world. And his main research areas, the main research areas of applications are demography, marketing, and so on. And he has numerous publications, journal publications, books, book chapters, and he has been involved in and is involved in numerous projects. So, topic for today, ladies and gentlemen, is network mining. And the contents are elementary notions of networks and graphs, measures of centrality and community detection, link prediction, attributed networks, multi-layer or multi-layer networks. And you know, when I was typing this here, I thought maybe some type of a typo, because I have never heard these things. So then I Googled it and I found that community detection is very much there, local community detection. Over to Dr. Pedro Campos. So, ladies and gentlemen, I will now escape and I will also stop sharing my screen. And I will now allow Dr. Pedro to share his. In the meanwhile, I would like to welcome Ms. Sadaf Malik, Dr. Asifa Kamal, Ms. Kamal Aslam, my own team member. Yes, Pedro, please go ahead.
Thank you. Thank you very much, Saleh, for this introduction, introduction one more time. I'm going to share my screen, and let me also welcome you all to this last workshop of this series of the Introduction to Data Mining and Network Mining workshops. So can you see my screen?
Yes.
Okay. So I'd like to start by maybe going a little bit back from where we was previously in the second workshop. So again, all materials are available here. So I can send it again to you for those who are attending today by chat.
And Dr. Pedro, if you could also send to me all slides of all three, that would be kind.
Yeah, of course. Everything is there on this link that I just send you by chat, but I can also email you kind of a zip file containing everything.
Thank you so much. Thanks.
Okay, you're welcome. So all materials are here. Of course, if you don't have the slides, but okay, so the slides are for those who attended last workshops. The link is exactly the same. So just go there and you can find the new slides for today. So we started more than 1 month ago with the first workshop of this series, where we introduced the topic of data preparation. So in the scope of data mining, this is a very important step. And I think that everybody knows, everybody is aware of this. For those who are already working in statistics or data mining whatsoever, that maybe more than 70 or 80% of the time that we spend doing data analysis is spent on the data preparation step. So this is a very important step. That's why we have dedicated a whole workshop only on this topic. We focused on issues like missing values, outliers, symmetry, normality, how to deal with those kinds of things, and so on and so forth. So that's a very important step. Then in the second workshop, we went to the modeling and evaluation step. So in that model, CRISP DM, that cycle, that virtuous cycle that we should, of course, follow. It's not compulsory, but it's kind of an advice that we follow this kind of cycle. So starting by the business understanding, data understanding, then do data preparation. And then what follows is modeling and evaluation. So what is modeling and evaluation? This was the topic for the second workshop. This is where we start by knowing the algorithms, the models and the algorithms. We have distinguished the main algorithms in between supervised and unsupervised learning algorithms. We focus on two specific algorithms, and then that's what we have done. So for today, we are going to focus on a little something that it's a little bit different, exactly because the type of data that we are going to use is different. So that's why we have introduced network mining here. It's not because this is a completely different issue. No, it is not. We are also going to do data mining, but the type of data that we are going to use to do this is what we call complex data. So complex data is data that is not the type of data that we are used to use, like what we call the traditional raw data in the table with rows and columns, rows that represent individuals or observations or hypotheses, and columns that represents variables or attributes. Now, in the case of networks, this is completely different. We are not going to have this kind of data. We can also have attributes and individuals, but the structure of data is basically different. So that's why we're going to talk about this today. So of course, not all complex data is network data. We also have other types of data, like, for example, audio and video, text. All this type of data is also complex, such as network data. So we are going to start by elementary notions of networks and graphs. Then we are going to introduce some measures of centrality and community detection, and we will have some practice with the new software, Gephi. I don't know if you know Gephi, but
no.
we are going, no. So I'm sorry, maybe I should have told you this before.
No problem. Actually, it's very exciting to keep learning new terms.
Okay, so Gephi is a free software. We use it in my university to teach network mining as well. It's a very introductory software, so it's very easy to install. You can install it in maybe less than 1 minute. So I'm going to talk about this later on, and we are going to make some practice with this software. Of course, we could also use R, like in the previous sessions, not RapidMiner. RapidMiner is not, we cannot do nothing there because it cannot deal with the network data, but R is very useful for network mining as well. But well, I decided to use Gephi. I think it's maybe preferable. It's very easy to use, and also it's very visual. So I think that we could do this here today. Okay. And then we will end with some extensions to the workshop, like I would say more advanced topics such as link prediction, attributed networks, and multi-layer networks. So having said that, let me just say that please don't have very high expectations about this workshop today. So I'm not going to enter in detail in many topics in network mining. So we are not going to do data mining like we have done before. So we could do some clustering or some prediction. And indeed, that there are many applications of clustering. For example, what we are going to do with community detection is a way of doing clustering in networks, which is although it is a little bit different. And for predictive tasks, we can do link predictions, but we are not going to enter in detail in this topic. So let me just give you this this disclaimer. Okay. So I don't know exactly if you are aware of network mining. So network mining is maybe a topic that we can sometimes confuse with social network analysis. So in a certain point of, let's call it science, maybe there are no differences between social network analysis and network mining. Maybe when we talk about social network analysis, we are more focusing on the social issues of networks instead of, let's say, engineering or maths or graphs or whatever. Maybe sometimes it's not, but generally speaking, sometimes academics, they confuse or they mixed up the concepts of social networks, social network analysis and network mining. So I have got a quote here from Moreno that wrote something in the New York Times back in 1933, so almost 100 years ago. I'm going to read it because I think it's important. So we sometimes say that this that's Moreno was the person that maybe started a new scientific area called sociometry. Sociometry maybe gave birth to what we call today social network analysis or network mining. So so what he wrote there was the following words. So if we ever get to the point of charting a whole city or a whole nation, we would have a picture of a vast solar system of intangible structures, powerfully influencing conduct as gravitation does in space. Such an invisible structure underlies society and has its influence in determining the conduct of society as a whole. So this sentence, or this couple of sentences, is maybe trying to join together, you know, the representation of something, because we are talking about representing structures, like, for example, a city. But what is underlying these structures is something that is very similar to the solar system, because we have, you know, nodes like the planets or the central star, and then you have connections between the planets, for example. And this metaphor is maybe the beginning of sociometry dealing with social networks.
Okay.
So nowadays we say that SNA, or social network analysis, is a process of investigating social structures through the use of networks and graph theory. So there are many different people and areas working with this kind of topic that now we can call a science. But this science brings or connects other sciences like physics, for example, or economics, or even health sciences, sociology, and so on and so forth. So indeed, this is a very big, I would say, hat for many different fields. So the basics of social network analysis are indeed networks, is to represent the phenomenon that we want to study as a network. And this network is characterized in terms of nodes and ties. Nodes that can also be called individual actors, people or things in the network, and the ties that are also called edges or links that represent the relationships or interactions that connect those nodes. So those nodes are, for example, people like us, we are here, and the relationships between us or among us, these are represented by the ties. So this, right. This definition, you can just go to the Wikipedia and just read it there. It's there.
Right.
So some examples of social network analysis, some examples of networks is, for example, this social structure of countryside school district, where you can see the links between, so all the node, every single node represents a student in a school or in different schools. And the color of the node represents a particular level or a grade or of the school system. For example, the pink, it's assigned to the 7th grade, the purple is the 8th grade, the blue is 9th grade, the red is the 10th grade, green is the 11th grade, and the yellow is the 12th grade. So as you can see, there is a kind of a nested structure where we, in a certain extent, can see communities. It makes sense, for example, that the students in the same grade are connected and are more connected because they belong to the same grade than, for example, if they belong to different grades compared to if they belong to different grades. In that case, it's maybe more difficult for them to be connected. For example, you cannot see many ties between the pinks and the yellows, because the pinks corresponds to the 7th grade and the yellows are those from the to 12th grade, it does not mean that it is impossible. It only means that maybe it's rare, it's a very rare phenomena. However, you can see some links, some connections between the pinks and the purples, although they are from different grades, but they are from, very close grades, from 7th and 8th grade.
Right.
And the same happens, for example, with 7th or with 8th and the 9th. We have some connections between the reds and the purples. So, and this is the basis of a structure, of the social structure that you can see in the social networks. And later on, we are going to see this in the scope of a statistical measure or a network measure that we call communities. So please interrupt me every time you need, because I don't know if I'm going to, well, these are maybe generalities, so I'm just making the introduction, but if you want to say something, please interrupt me.
I think it is very useful to get exposed to all these things. There's so much happening, and it's even the exposure is even if we can't go in depth, because for that we need many days. We can't do it in 1 hour or 3 hours.
Of course.
Exposure is valuable. I think it's and these pictures that you're showing, they're so interesting.
Thank you, Salaya. Yes, and it's funny because I'm going back to the previous slide. So the networks are exactly the same. As you can see, I'm going to switch between the two slides. The difference between them is that the previous one, the one that was I was explaining before, as I said, so each node is colored according to the grade where the student belongs. But then in this new network, what you can see, well, the network is the same, but now the nodes are colored according to the race, to the color of the people. Right. So what you can see here now is a completely different way of seeing the same network, but by color. So in this case, we have the whites, the blacks, and the mixed or others. And again, there are community. Sorry, we have communities. We have the yellow. We have the yellows representing the whites, with some connections with the others, of course. So that maybe now the mixture, I would say that maybe this is higher than before, but still there is some kind of segregation, that, let me call it like that. It's some communities, let's maybe better to call it like that. So it also happens like that.
Excuse me,
yes?
I have a question.
Please.
Yes, sir. From the left side, some nodes are not connected. It means that they are not associated.
That's right. Exactly. Like in the previous slide, the same
Yes.
4 nodes. Now we know who they are. They are both. 2 of them are from the 7th grade, and one from the 8th, and another one from the 9th. And these people are, for example, a mixed, 2 whites, and maybe this person from the 9th grade is black. Yeah. And they are not connected indeed, or at least they didn't say when they maybe answered with the questionnaire, or maybe, I don't know in what basis they have someone has been able to produce this network. So I don't know, maybe based on a questionnaire where they have just, okay, so please indicate who are the friends to who you talk in the breaks during the classes, or after the classes, if you are you a friend of her or him. So maybe it was based on a questionnaire, or maybe it was based on a direct observation. I guess, because I don't know exactly, so I have the reference here. It has been produced, it has been published by the American Sociological Association, by a guy called James Moody. And I think, I'm almost sure that this data came from a survey that has been made to the questionnaire that is being made to the students. So maybe in these 4 cases, and others maybe that are also there, these people replied that they have no ties, no connections. That's right.
Thank you, sir.
Okay.
And one more question. Generally speaking, why are these 4 that are not connected on the left side of this picture? Like what decides on which side of the picture these are going to be?
So the side of the picture does not represent anything special. So this is only a way of representing the graph. You know, in this case, the network of the connections of the students. So they could be in the other side. It depends. We are going to see later on with the software that there are at least 10 different ways of, you know, optimizing the representation of a network. These are based on the based on mathematical models of optimization for the visualization.
Right.
But this is a very good question. Why are they there and not, for example, on this side of the screen, of course.
Okay, thank you.
Well, Pedro?
Yes, please.
Does this mean that for a particular problem, these 4 individuals are somehow excluded? You know, they have no such relationship with the rest of the one. So they are excluded from the particular problem at hand, I believe. Does this...
Well, I wouldn't say that they are excluded, because for a matter of representation, they are not connected, but they are still in the network. This is what we call we have a name for this kind of nodes. These are not connected nodes. They are not connected. So this is a not connected network. Sometimes when you have some network, in a network, some nodes that are not connected to the rest of the network, it seems we used to say that the network is not connected. You have different parts of the network, so they still belong to the network, although they are not connected. It seems contradictory, but it is not in that sense.
I think it's not contradictory. I think that there may be some, in a real life scenario, there may be something like this happening, but that does not mean that those individuals are not important. The ones who are not connected, they may still be important. So that's why they are not excluded from the...
Yes, might be isolated, or you can say, is there some social boycott?
Yeah, because indeed, in the network science, sometimes we also have we are going to talk about this later on, the attributed networks. It means that we are not only going to look at the structure, but also to the contents of the nodes. So I mean that
Pedro, what is used for making these connections? What are the parameters for connecting them?
Yeah, okay, so in this case it's only the number or a direction. I'm going to show it later on. So it's a kind of a matrix, a 2x2 matrix, where each person indicates who are their friends. And so this is kind of a symmetric matrix in case there is no direction, or in case there is a direction. For example, if A is a friend of B, meaning that, for example, B is not a friend of A. In this case, there is a direction in the friendship. Usually you don't have direction in the friendships. For example, in the Facebook network, there is no direction, but you can see here that there is some direction. I don't know if you are able to see the arrows. Yeah. So it means that, for example, here, based on this survey, maybe the question was, please indicate someone that is your friend.
What I was wondering, that maybe they are isolated for people are different, because the parameters we are measuring, they may not apply to them.
I think that maybe if the answer was just please indicate I don't know how many 5 friends in this school that are your friends, and indicate what are their grades or what are their colors, for example. If it is the case here, and if they are not connected, it means that maybe they didn't answer anything here, because they say, okay, so this is not compulsory. If they have no friends, if they have no ties.
That's what I meant. It doesn't distort the figure. It depends upon what you are measuring and what you are using in this figure.
Yeah, that's right. So that's right. What I was going to say is that in some more, I would say, more advanced fields of study in network science, you have also you can also analyze the attributes of these of the nodes. So maybe we could understand why these nodes have no connections. We could try, for example, to make a model like a regression model to understand or to predict if, for example, a new person is going to become friend of another person or not.
Right.
Based on the
Right.
existing attributes. So,
right.
but for now, we only have connections. We don't have anything else.
Yes, I think we can carry on.
Okay. So I'm still with examples. So this is another example of the United States election in 2012. This is a very famous example because this is what we call bipartite network. Bipartite because, or two-mode, can also be called the two-mode, because in this case we have two types of nodes. And the nodes are expressions, you know, phrases, and people and persons. And it's good because if you link all these words, like in a word cloud, you can see the links between persons and expressions, and try to see what are the links between them. For example, Barack Obama is somewhere here, and then you have Mitt Romney, the other candidate, and other candidates here. So this is another possible application of the network. This is another example. We are going to use this example today. This is the Zachary's Karate Club network. And these are the communities that have been detected there. So every node represents a person in that karate club. And this is a friendship network of this club. As you can see, the structure of network is important. For example, you can find some people that have that are more popular, like A1, for example, or A34. If you just compare A1 with A34, these are two different people in the network, in the same network, but A1 is connected with this kind of people. We can say that maybe is a center of a group of persons, but A34 belongs to another group. Of course, that both groups have connections, and as you can see, there are connections among them, maybe through other persons. And if we take it like that, I mean, if we color these links, we can see that there are maybe two groups, and A1 and A34 are what we call the hubs, you know, the centers of these groups. So it's very important to look at the networks and to analyze them also by not only by communities, for example, like here, but also by computing some measures that are important in the network, like centrality measures. We are going to see also this today. So let me now start with some basic concepts of a network. I'm going to use the word graph, which for me is more or less or completely similar to network, although maybe we can see that the graph is the representation of a network, but I'm not going to pay attention to this difference. So let's start with a graph. And the graph is defined by, as we have said, a set of nodes like the ones that you can see here. For example, we have A, B, C, D, E, and then a set of ties, like the ones that we have here. Okay, so if we link the nodes with the ties, we have something like this here. So A is connected to B and to C, then C is connected both to D and to E, and also D is connected to E. So again, so nodes, we can call them also actors or vertices, and ties, we can also call them links or edges or even arcs. It represents, for example, friendship or flows or whatsoever. So maybe one of the most important concepts, I would say basic concepts of networks is this concept of the direction and the concept of weighting. So the direction has to do with the direction of a link. For example, the one that you can see here, this network, it was the previous one, is undirected. So it means that there is no direction between the relationships. For example, this could be a friendship relation. In Facebook, you don't, if two people are friends, there is no direction. Because for two persons to be friends in the same network, they have to agree. And so that's why there is no direction. But this is in Facebook.
Can I interrupt here? I think if
Yes,
you
of course.
analyze it in such a way that who sent the friend request, then I think you can have a direction.
That's right. In that case, it could be like that. I'm sure that in Facebook that they do this kind of analysis. But generally speaking, the Facebook network has no direction. The links have no direction. At the end of the day, you just say that, okay, so A is a friend of B. But there are other examples where you have a direction. For example, in Twitter. In Twitter, you follow someone that maybe cannot follow you. So it's different. So in this case, you can have, for example, the one below. I'm sorry, it's not this one here. I think there is some confusion here, because the one that I wanted to show is this one here. So you have the direction here, A to B, and also B to A, for example. But in this case, A follows B and B follows A. But in C follows B without B following C. So it's a matter of direction. I think that the boxes are wrongly placed, so the box should not be like that. Anyway, I think that it's easy now to understand that. So this is an undirected network. This is a direct network. So we are talking about direction here. Now we are going to talk about the weights. So what are the weights? The weights are how strong are the connections between the nodes. So this is related to the strength of the ties.
Right.
So you can put values on the ties. For example, here the link between A and B has a strength of 1, but the link between B and C has a strength 3 times greater than the other one. So it means that this network is undirected. So you have no directions, but this is a weighted or valued network. And this case here, the last case, is a directed network and is also a valued network, because you have strengths here. You have different strengths. You don't have numbers here, but you could, of course. Sometimes instead of numbers, we represent the strength by how thick, the arrows are. So these are two important concepts.
This thick one is very interesting. I mean, it's attractive, but the problem is that you would not be able to differentiate easily between, for example, 3 and 4. In the numbered one, you can have you can differentiate.
Yeah, you are completely right. Of course, it should be, the numbers should be there. It's not very easy to understand them. Yeah. There is also another important concept, is the concept of having more than one types of nodes in the same network. So basically what we know is that all the nodes are the same. For example, such as in Facebook, every people are people. They are just persons like us. And okay, we have friends. A can be connected to B and B connected to A. So it does not make any difference. But sometimes we have what we call the two-mode or bipartite networks, when we have different types of nodes. What are the different types of nodes? Well, it's everything that you want to distinguish. For example, sometimes we have networks that are connections between, for example, persons and companies. And we want to make connections between who belongs to what. Because the same person sometimes can work for different companies, like, the people that are in the board of the administrations. Sometimes they belong to the administration of the board of the administration of company A, such a big company, for example, multinational or something like that. And also it can belong, the person can also belongs to another board in the company B. So in this case, we can have different types of nodes representing people, and also nodes representing companies. For example, here, B and E, for example, can represent companies. So the person A belongs to the board of company B, such as C And then D is connected to E, such as C is connected to E. So it's sometimes it's a little it can make sense to use this kind of differentiation between nodes. We call this bipartite. Of course, we have two modes. Why not having three modes? In this case, we have three types of nodes. So now we can extend this concept of different nodes. So this is my example of having people working in different companies. For example, person number 1 works to A and to B, and 2 works to A and to B, and so on and so forth. And then what you do sometimes is to make a projection from this network to this network here, where you flatten the layers. So you have kind of two different types of, not exactly layers, but nodes. And two persons are connected if they are connected to the same companies. For example, 1 and 3 are connected. Yes, of course, they are connected because 1 is connected to a company for which 3 is also connected. For example, 1 is connected to D, 3 is also connected to D, and so 1 is going to be connected to 3. So now in this network, you don't have companies, you only have individuals, meaning that the individuals are belong to the same network if they belong to the same board of the administration in the same company. So we made a projection from these two-mode networks to a one-mode network. Of course, we made a projection of individuals. We could also have done a projection of companies, and instead of having numbers here, we could have letters using the same concept.
And Dr. Pedro, I want to ask you this word mode. I mean, in basic statistics, the word mode has a different meaning, right? So it's
yes, of course, that's right.
Confusing.
Yeah. Mode has nothing to do with statistics in this case. So mode is the type of node. I don't know exactly why they call it mode. Maybe I prefer to call it bipartite or unipartite, but well, I think that mode is most used now in social network analysis. Yeah. Okay, so now let's see how we can represent the networks. And this is the basic way of storing information about networks. We use what we call the adjacency matrix. So adjacency matrix is a matrix. If we don't have value networks, so if every link is only 0 or 1, meaning that two nodes are connected or not. So in this case, and if the network is undirected, like this one here, so we call it undirected binary. So it's binary because we have a link or don't have a link. And this is the way how we can represent the network. So as you can see here, for example, there is a link between A and B. So let's put it there, a 1. And there is no link between A and anyone else. So A has no links in the same row. We could put a 0 there, but usually we don't put nothing, meaning that, okay, so the cell is empty, meaning that there is no connections with anyone else. And so that's the way how you can represent. So then we also have B and A because this is a symmetric. So this matrix is symmetric, as you can see. This is a symmetric matrix. It's a 5 by 5 matrix. And so you have a connection between C and B, of course, and another one with C and D, because you have C and B and C and D, and that's the case here. So basically, an adjacency matrix is represented like that. So every single number there is 1. If there is a link between the Y and the J, meaning the row and the column, and is 0 if there is no link, or 0 or just empty. So this is an undirected binary. So now if you want to have a directed binary, so the matrix is not symmetric anymore. And this is the case. For example, you have a link between A and B and another one between B and A. That's it. Then you have a B, C to B, but not a B to C. So you have C to B, but not B to C. And so that's a different way. So the matrix, you still have the same way to store the information. The only difference is that if the networks are directed, the matrix is not symmetric anymore.
Right.
So the only difference between this case here and let me go back again. In case, for example, you have a weighted matrix, a valued matrix, the only difference when you want to store the information is that instead of having zeros and ones, you will have values in the matrix. So I don't have this example here, but I think you can imagine it, right? So instead of having just a binary network, if you have a valued network, the only difference is that now, if you have a valid matrix, well, the numbers start appearing here instead of just ones.
Okay.
Well, Pedro?
Yes, please.
Can you please switch to the previous slide?
This one here?
Yeah, in case of directed binary, you know, like for example, these nodes represents the human beings, right? People. If
Yes.
A is a friend of B and B is a friend of A, okay, it makes sense. But in case of B, C to B, C is a friend of B, let's say, in the case of direction, but B is not a friend of C. I mean, how this can be interpreted?
Of course, in terms of friendship, it makes no sense. So in this case, maybe it could be Twitter, for example. If you follow someone that does not follow you, so
C follows B, but B doesn't follow C.
That's right.
That makes sense.
Yeah,
Thank you.
You're welcome. Yeah, it could be an example of a Twitter. Yes. Okay, these are other ways to store information. So instead of having an adjacency matrix, you can have an adjacency list or an arc list. The reason why we do this is because it's computationable, more efficient to use lists instead of matrices. As you may know, I guess sometimes it's, imagine that you have a very, very wide network of, let's say, 1,000 nodes. So if you have 1,000 nodes, to store the information of 1,000 nodes, you need 1 million cells in a matrix, so a 1,000 by 1,000 matrix.
Right.
And sometimes it's not very comfortable to do this.
Right.
Yeah, so instead of this, you can use an adjacency list. For example, here, A to B. So this is exactly the same network, the symmetric one. So we can do it like that. For example, A to B, then B is linked to A and to C. That's what we have here. C is linked to B and to D and to E. So you have C, B, D, E. And the arc list is maybe even more efficient. You only have pairs of nodes, and every time you have a pair, it means that they are connected. So for example, here you have AB, BA, BC, CB, CD. So all these pairs correspond to links. So the most pairs that you have, the most links that you have in the network. And for valid networks, you need a third
Pedro,
column.
You said that this is more efficient. So I know nothing about computing, but I was just wondering, isn't this one the adjacency plot? Is this not more efficient?
Then the arc list. I think that the arc list. I think that the arc list is more efficient than the agency list.
Okay.
So it depends. And also there are different softwares. For example, Gephi, we are going to use Gephi. Gephi uses the three different ways of reading the data for networks. But for R, for example, I use a package in R called iGraph. iGraph, as far as I know, only uses the matrix, the adjacency matrix, and the arc list.
Okay.
It does not use the adjacency list. I'm not sure, but I think I never use this one here. I only use the arc list and the adjacency matrix. So it depends on the type of software that we're using. For example, I don't know about Python if they use these structures, but these are indeed the most used structures to store information about networks. Yeah. So what are the factors that influence the flow of information in a network? So now we are going to enter in more, I would say, important knowledge about the network. Basically, these are the topology. So the topology is a very important issue in the network because it deals with the way how the network is configured. So you can have a more central network or centralized network like a star, or I don't know, you can have a random network completely different one. So the topology is important, and also the time, how you can spread information through the network. Because basically a node cannot pass information to another node if it is not connected to it, or if it has not received any information from it. Another important concept is the one of communities. I think I have introduced this one before. So basically, if you don't see these blue circles, you cannot imagine that there are some communities here, but they exist. They are kind of a subgroups, and these are important to be identified. We have talked about subgroups or communities before, just in the first or second slide when we introduced this example of the social structure of the countryside school district. So I'm not going to talk about it anymore now. And now let's enter a little bit in the network metrics. So I'm sorry for that. Maybe it's a little bit, how can I say, extensive, this part of introduction, but we need to do this. Because these are maybe the most important metrics to measure the type of networks. Reachability, for example, is how you can access one node from the other node. So it's a wide concept. We are going to deal with this in the next slides. So, for example, let me start with the notion or the concept of a path. A path is just a sequence of nodes and links that start at one node and end at another node. And there is an important issue here, is that in a path you never go back or visit the same node twice. For example, a path could be here A, B, C, and D in that sequence. For example, A. I think you can see my mouse here. So A, B, C, and D. So this could be a path here. A walk. So a walk is a different thing, because in a walk you can go back or visit the same node. For example, you could go from A to B to C, back to B again, to C and to D, doing something like A, B, C, B, C, D. And this is what we call a walk instead of a path. So this walk, of course, contains a path, but a walk are exactly the nodes that, for example, if you are dealing with flow of information, imagine that these are people inside a company, and you are sending a document or an email to A that sends an email to B, then the B sends an email to C, back to it answers only to B, and to C again, and then to D. So you can imagine that the flow of emails could be represented as a network, like a walk. So that's another possibility of having a network here. So sometimes it's important to define this kind of concepts. And a cycle. Okay, so a cycle is like a path. So, but the only difference is that the path starts and ends in the same node. For example, a path can be C, then D, then E, and back to C. So this triangle is a path. And for example, nowadays in the network science, these kind of things are have a very strong interest in them. So there are many people still studying this kind of cycles. Sometimes we call it subgraphs or motifs, because these subgraphs or motifs can give you some insight about the structure of the network. For example, there are people studying, fraud detection. in companies, in banks, basically by, for directed networks, these are undirected, but imagine that, for example, we are talking about sending money to. So each link represents a bank transfer, for example, from C to D, then D to E, and E back to C. So these are bank transfers. They don't have to have exactly the same amount of money. Imagine, for example, that C transfer, I don't know, 1,000 euros to D, then D transfers 500 euros or dollars to E, and then back another, I don't know, $700 to C again. So no matter the amount of money that you are exchanging in this network, but you have a cycle that starts and ends with C. And this motif in the network, if you have a network of bank transfers, sometimes based on that, you can make this kind of compliance analysis that some of the banks can do to see in what extent they have fraud or everything is okay. So these are the kinds of things that you can use to measure fraud detection. So what is distance? How can we compute distance in networks? This is a very easy way. Basically, the distance is the number of steps between a pair of links. Let me give you an example here. For example, oops, sorry. So A, for example, this node here, the distance between A and this nodes is 1. I'm sorry. Let me do it again. And for these nodes with a different color, the distance is 2. So these are the names of nodes, you see. This is the node number 1, node number 3. So, and I'm using A as a kind of a different node for you to see we are computing the distance between these nodes and the other nodes. And for the red nodes, now the distance is 3, for example, from A to 6. Let me count it. So 1, 2, 3. That's right. Or 1, 2, 3 to this one here. So and 1, 2, 3 also here. And for the other nodes, the distance will be 4. So basically, the distance between a pair of links, between a pair of nodes, is measured by the number of links that you have between these two nodes. And you can also have this one here. So the steps or the links, when you count them, are exactly a measure of a distance. So in networks, it's very easy to compute the number. Of course, you can also use, if you have weights that can represent, for example, distance. If you are talking about roads, like streets or in a map, you can count the distance between two nodes by computing the amount of kilometers, for example, between this pair of nodes. But if you have a basic structure in a network just with the nodes and links, so then you can use only the number of links. So this is the notion of distance. So now, what is the diameter? So diameter is a very important concept of a network. It computes the shortest distance between the two farthest nodes in the network. For example, here in this network, maybe it would be very difficult to see if I would not have represented this path here. So this is the Zachary Karate Club network, the one that I've showed before and that we are going to use later on in Gephi. So these are persons that have relationships or friendship, for example, or they belong to the same team in the karate club, or I don't know, whatever. And so the diameter of this network, if you compute all the shortest paths, so maybe I should have also introduced the concept of shortest path. So the shortest path is the shortest path between two nodes. It's the shortest way of going from one node to the other node. And if you compute all the shortest paths in the network, the shortest distance between the two furthest nodes is what we call the diameter. So in this case, the diameter is, let me compute it. So the diameter is, for example, this one here, this path. And now let me compute the distance between the two furthest nodes in terms of distance. So it's 1, 2, 3, 4, 5. So the diameter of this network is 5. So we have used R to do this.
Very interesting.
Sometimes it's important to know because the network seems so huge, so big. And then when you look at the network and you compute the diameter by doing this kind of very, very simple computations, you can do it automatically with a package like iGraph that we have used here. It's, you know, it's in this case, it's 5, isn't it? 1, 2, 3, 1, 2, yeah, 3, 4, 5. And then you can compare networks, okay, based on this. So now let's go deeper in terms of the network metrics. Let's talk about density. So the density of a network is just the ratio between the number of existing network links and the possible number of network links. For example, here in this network, you have 4 nodes. So 1, 2, 3, and 4. All of them are connected except 1 and 4. So 1 and 4 are not connected. So the density is 1, 2, 3, 4, 5 over 6. So there are 5 connections over 6 connections that are possible. So density is 5 over 6, it's 0.83. So this is undirected network. So if you use a directed network instead. Yes.
Dr. Pedro,
Yes,
how do you
please.
get 5 over 6? Is it not going to be 4 over 5? 5?
1, 2,
Okay, 1, 2,
3,
3, 4, 5.
4,
Okay.
5, yeah.
Okay, I got confused, sorry.
Okay. And in the example below, it's even more difficult because now you have a directed network. So you can have 2 arrows in the same direction, for example, from 1 to 2 and from 2 to 1. So if you take the same network, but with directions, now we have the same 5 links, but within 12 overall that are possible. So we had 6, but in 2 directions, they will become 12 because we have 2 in all in both directions. So in this case, the density, in the case that where the network would be directed, the density will be 5 over 12. I mean 0.42. So the density of the network depends also in the type of direction of the network, if the network is directed or undirected.
Is it good to have a high density or bad?
Well, it depends, of course. Usually we are going to say, I think that my last slide is going to be about that. So you are going to classify all the possible networks. And we used to say that in real life, networks are not very dense. So it does not mean that it is good or bad. It's reality. Networks are not very dense. So the density is low.
Okay.
And we can talk about the distribution of the degree of the nodes. So the degree is just the number of links that are connected to, maybe it's going to be the next concept. So let me go there. Yeah, okay. That's exactly the degree. So one of the most important metrics that you can talk about is centrality. Do you remember in the Zachary Karate Club network, we have those nodes that are important hubs between 2 different groups or subgroups in the same network. So we can compute the centrality of each network because it identifies the nodes that are the center of the network, and maybe they can be important. Imagine for example that you are dealing with a group of people. If you identify those that are most central, maybe they are most important. I mean, in terms of marketing purpose, for example, you know, in social media, sometimes you call them the influencers. Do you know this name? The people that talk about, for example, a new perfume or a new I don't know object of fashion, a new I don't know dress or something like that. For example, an actor or an actress, they can be very strong influencers. So when
like when we say trendsetters.
that's right. Yeah,
Mm-hmm.
that's right. The fashion. Yeah, that's right. It's important to identify those who are more central in the networks because they have more connections. Like, for example, in my country,
as we have Dr. Salha within the PISTAR group.
Yeah, that's right. you are right.
Thank you. Thank you very much for that.
I was going to say, I was going to give another example. The example of in my country, you know, I don't know if you heard about the soccer player Cristiano Ronaldo. I think that Saleh is maybe more famous than Cristiano Ronaldo, but but sometimes we used to say that who knows Cristiano Ronaldo knows the world, because he's the center of he has more than, I don't know, millions and millions of fans and millions of links in the social network. So if you want to advertise, for example, I don't know, something or a cloth or something like that, or a new fashion, you just go there and ask them to make an ad for the TV, because it's very central. So centrality is very important. Okay, so that's what I want to say.
He's very well known. I think he's known all over the world. Yeah.
Yeah, I think so. Yeah. There are basically three, well, there are more than that, but maybe there are the three most important measures of centrality. I have them here: the degree centrality, the closeness centrality, and the betweenness centrality. So let's start with the degree, which is a very, very easy way of computing centrality. So centrality degree or degree centrality is the simplest of all the centrality measures. It's only computed by the number of links that are incident on a node. For example, if you take a look at this graph here, so we call this is a star network, because you have these nodes overall, around a central node. So what we have here inside this, I don't know if you can see this. Maybe the numbers are too small.
We can see it.
Okay, I think I can enlarge the image like that.
Yes,
okay,
now it's better. Thank you.
Okay,
That's
so
good.
what you see here inside these rectangles are the degrees of each node. So each node represents a person, for example. So each node's degree is 1, as you can see, and the central node's degree is 7. And why is 7? Because the central node has 7 connections, 7 links, 1, 2, 3, 4, 5, 6, 7, and all the others have only 1. So this is degree. This is the degree of each of the nodes. For example, in this this other example. So of course the idea is the same.
This diagram is very interesting.
Yes, it is. So you have yeah. So it's important to know, and when you look at the network, these are the kinds of things that you must pay attention to. For example, I remember that during the vaccination to COVID-19, people were concerned about the centrality of the nodes. So the nodes are the patients, and the more central they are, the more need to a vaccine they have, because if they are central, it means that they are very exposed, because they can be the hub of the disease, because, for example, if the 7 can be a medical doctor or a teacher, because it has a strong exposition to other people. For example, if the 1 infects this node here, it's not a number 1, this is the degree, but let's call it A. The node A infects the central node, then the central node, because it has a connection with this node here, can also infect that one. So that's why we need to vaccinate the nodes with higher centrality. That's one example on how centrality can be important. So this is centrality. This is the degree for the other nodes in this network. So it's very easy to see that these here I have 3, 3, 2, 2. And this is what we call a circle network. It's a very strange, this is a very rare network. Sometimes it happens. Every node only has connections with its neighbors, not with the others. And so the degree is the same for everybody's too. So this is the centrality degree. So it's maybe the most easier way. So now let's go to something a little bit more complicated. So the centrality, no, sorry, this is the same one. So this is the way how we compute. This is the equation. So let's call it D Ni, the degree of node Ni, which is basically the sum of all the links Xij, where Xij are the the numbers of the adjacency matrix, like we have introduced before. Sorry about my dog. It was.
It's all right.
It's always the same thing. Sorry. Okay, in undirected networks, that's not a problem. Everything was undirected here, as you remember in the previous slides. But if you have directed networks, you can distinguish between the incoming links and the outcoming links. And so we can also compute the in degree and the out degree. So it is, I think this is a very intuitive definition and very easy one to understand. So the in degree is the degree only if you count the inbound links, the links that enter in your for which the direction is the incoming direction, and the out degree is the degree if you compute only those that are the outbound links, so the ones that go out from with a direction out from the existing link.
Right.
So okay, I don't know if is it someone was going to say something? No, anyone was going to ask anything?
I think it's all right. You can continue.
Okay, so let's make a very short practice in exercise 1. So given the network defined by the following nodes, so this is a remember, this is an arc list. You have the pairs of nodes. So you have 1 connected to 2, 1 to 3, 2 to 3, 2 to 4, and 4 to 5. So this is an arc list or edge list, which is exactly the same. So now we have 2 things to do. First, represent the network with a graph, and then compute the degree of each node. So I don't know if you want to have some time to think about, but I think this is very easy. This is a very easy task. So I have the answer in the next slide. So one is computed.
Dr. Pedro, yes? This will depend on the amount of time that you have. It is
well,
3:30 here. So if you think that there is time, then we can try to practice. Somebody else can.
Yeah, I think that we don't have much time to do this.
Okay, then we can do it in the CLI session. Dr. Thomas has already been conducting CLI sessions, so we can do it then. So you can just demonstrate.
Okay, thank you. Thank you. So the answer is this here. So 1 is connected to 2. So these are the numbers of the numbers of the nodes. 1 is connected to 2. The 1 is also connected to 3. Then 2 is connected to 4, and 4 is connected to 5. Let me go back. So this was exactly the edge list that we have. So this is the answer for A. Then the answer for B is the degree of each node. So now in each node, this is the number of this is the degree. For example, the node number 5, the degree is 1, meaning that there is only 1 link connected to this node. And for example, for the node number 2, the degree is 3, because we have 3 links connected to node number 2. It does not matter if they are incoming or outcoming links, because this is an undirected network. So this is a very easy exercise, of course, that if you have a network of 1,000 nodes, it makes no sense to be computing this by hand. So there is software that does this by you. So let's move to the next network metrics, the centrality closeness. So now it's a little bit different. We are not going to compute centrality based on the number of links, based on the degree, but based on the distance between the nodes. So basically this closeness centrality is the inverse of the distance to other nodes. So the idea is to have a measure of the closeness of the network, how close the network is. Because you can have central nodes without the nodes being close to the others. I think that this gives us a very good perspective of how close the network is. So I have an example here. For example, for the same networks, we have computed the closeness, the centrality for all the nodes in the network. And for example, those here in the first star networks have a closeness centrality of 0.54. So how can we compute this 0.54? So it is basically the inverse of the distance between a particular node and all the nodes in the network. So for example, in this one here, if we compute the distance, for example, to this node, to the node in this left here, so the distance is 2, because if you are here and you want to reach this node here, you need a distance of 2. So first you need to go to the center, and then in the second step you are there. So it's a distance of 2. And the same happened to the other nodes. So for example, if you want to go from here to here, the distance is also 2. So if you want to compute the distance from this node to the other nodes in the network, it will be 2, you see, 2 plus 2 plus 2 plus 2 plus 2 plus 2. So it's 2, 4, 6, 8, 10, and 12. 12. But there is another one. There is the central node, which is 13, because the distance between this node and the center one and the one in the center is 1. So the distance between all the nodes and this one is 13, right? So now using this closeness centrality, which is the inverse of this sum, you will get 1 over 13. So 1 over 13 should be the centrality closeness of all the nodes except the central one. Central one is only 1.
But why is it being multiplied by 7?
This is a good question. That's right. So in the previous slide, I didn't mention, but sometimes we use a normalized measure of the distance given by that number multiplied by g minus 1, where g is the number of links, is the number of nodes. I'm sorry. So if you have here we have 6, 7, 8. We have 8. I'm sorry, 3. How many nodes do we have? 1, 2, 3, 4, 6. Yes. Yes, we have 8 nodes. Yeah, 1, 2, 3, 4, 5, 6, 7, and the central node 8. We have 8 nodes overall. So G is 8. The G is the number of nodes is 8. So if you want to normalize this distance, because the distance, this centrality can depend on the dimension of the old network. So you need to multiply it by G minus 1. So G minus 1 is 8 minus 1 is 7. So that's why we have 0.54.
Can you explain again, how do you arrive at 13?
Yeah, okay. So, yes, of course. We have, according to this measure, so the centrality is the sum of the distances for a particular node to all the nodes in the network. And then after summing all those distances, we need to compute the inverse of this number. So for example, let's focus on this node here. I don't know the name of it. Let's call it the node A, for example. So the node A, the distance between this node and, for example, this node, the neighbor node, the distance is 2, because if you want to reach from A to B, for example, let's call B this node here. You need to go first to the central, and you take one step, and then again to the other node. So you will take 2 steps. So this distance between this node and this here, it will be 2. And the same will happen, for example, to this node here. The distance between this one and this here will also be 2. So 1, 2. And the same here. It's going to be 2. So the distance between this node and this one is 2. 1, 2. So for all the nodes in the network, the distance between them, except the central node, of course, I'm just focusing on this node here. So for all the nodes in the network, the distance between this node and all the other nodes is 2, except the one in the center, for which the distance is 1. So now let's compute all the distances. So it's going to be 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 1. So it gives 2, 4, 6, 8, 10, and 12 plus 1, it's 13.
Yeah, thank you. Thank you.
You're welcome. Yeah. No, it's maybe it's not so easy to compute because I don't have anything to show here. It's just my words. The equation is not very clear. Thank you. And now the last measure. But by the way, let me go back only for you to see that now it's not we're not talking about the degree. We're talking about how close are the nodes. And you can see, for example, that in this first example of network, we call it a star network. The closeness of the nodes is higher than, for example, in this circle network here, for which the closeness is very low. Well, it's not very low, it's lower than the previous. It's 0.4, as you can see. So the closeness of the nodes gives an idea of how close they are to the centers. And in this kind of star networks, they are very close to the centers. Whereas, for example, here the distance it's higher. So that's why the closeness is higher. Yes.
Here we don't have any center. I mean, at least the graph doesn't show anything in the center. So
not here. Yes, in the network in the middle, we don't have any center, but we have it here. You see, in this star network, it's like a star. You have a center of a star and everything else. So we have a center. So that's what I want to say. Right. Well, it's like a center, of course. In this case, it's completely symmetric, so you can call it a center. But in the network in your right, there is not, well, I would say there is not a center, maybe.
Excuse me, I think Dr. Ali Raza, you're writing something which is coming on top of the screen.
Yeah.
Dr. Ali Raza? Dr. Ali Raza, if you could please unmute. Dr. Ali Raza?
I'm calling.
Please, can you call them? Right.
Hello.
Something is being written on the screen, and it is showing your icon.
Sorry.
It's okay. If you could rub it, I'll be grateful.
Okay.
Okay, I can move on because maybe this is not a problem.
Yes, please.
Okay.
Please. Yes.
So, but I was just, yes.
It's not
it's
working.
Okay. You can.
I think you can do. If you undo, like because before there was something being written also, and suddenly it disappeared. So I think that you can do undo. No, in your.
Dr. Pedro, can I have
Yes.
one question?
Yes, please.
I think in your formula for centrality, the inverse -1 should be outside that bracket.
Oh yeah, I'm sorry. You are right. Yeah, it should be outside the bracket. Although so it's not. Yeah, you are right. So I think in the previous formula, It was, no, it was also wrong. Yeah, you are right. It should not be like that. It's not the inverse. It's not the sum of the inverse, it's the inverse of the sum. Yeah, you are right. Yeah, I need to fix it. Yeah.
And Dr. Ali Raza, if it is not being grabbed, I wonder if you leave and rejoin, maybe it will help.
Okay.
I don't know.
Okay, let me check it. I'm so sorry for that.
No, it's not.
It's all right, no problem.
Okay, thank you for this correction. So I'm going to fix it, and then I will place new slides with some, because I also found some typos there, and I'm going to correct everything.
Yes, I think
yes.
Dr. Ali Raza has left and he'll rejoin, but that written thing is still there.
So I think I cannot do anything for that. Yeah, because it's written in the screen, so I cannot do anything. I cannot. Let me maybe stop sharing and sharing it again, right? To see if it works.
Yes, maybe.
Yeah, I think it worked. Okay, so we don't have any.
Oh, it worked. Great. I think he was trying to understand the concept, and what he was writing, I could read some of it. I could read the word nasdeek, which means closeness. So he was actually trying to understand, I think, exactly what you were trying to
say. He was writing in Persian, I think.
It was a pity because he needed to leave.
Yeah.
And there was no need to leave. Yeah.
No, he's back.
Okay, you are back. Thank you.
Okay.
So everything is solved. Thank you.
Ali Raza, I just told him, Dr. Pedro, that you were trying to understand the concepts, because I and others could read one of those words, which was nasdeek. Nasdeek means closeness.
Yes. It was about the closeness concept. I just make a note there in Persian. I think I didn't think that maybe it's important in this slides. Sorry for that.
No, it's
okay.
Not
it's all right.
Okay.
So carry on, Pedro. Now you can carry on.
Thank you. Okay. So the third and last measure of centrality that you are going to see is betweenness centrality. So this is a different one, a slightly different one, because now the idea is not to compute how central only it is because it is more central, or because the distance between them or the others is less, but because now we are interested in knowing how. Let me use another word instead of betweenness, how intermediate your node is. So the betweenness centrality measures the number of shortest paths, that's the way how to compute it, between two nodes, G and K, that pass through a node I. So that's the idea. So for example, imagine that we are in the university, and Professor A is a friend of Professor B, and if a Professor C is very central in terms of betweenness centrality, it means that almost every friendships from A to B also pass through C. It means that, for example, I'm a friend of B, but I am also a friend of C. So before being a friend of B, I was a friend of C. So that's why maybe I am now a friend of B, because I've been introduced to B by C. So this is basically the idea. So I'm going to repeat the definition here. It measures the number of shortest paths between two nodes J and K that pass through node I. So basically we call it this centrality betweenness of the node Ni, and we sum all the for symmetric matrices, we only take care about J less than K, and this is the equation. So GJK Ni over GJK, where GJK Ni is the number of shortest paths between G and K connecting I. Okay, so the ones that go through this node particular, for example, if the Professor A is a friend of Professor B, but to go to B, you need to pass through C. So that's the kind of nodes.
And why do we divide by JK?
Yeah, and then we divide by the total number of shortest paths that just go from J to K. So this is kind of a ratio. So the higher it is, the most important the Ni is, or the node I is for the intermediation between J and K. So that's why we divide to compute a ratio.
Mm-hmm.
So for example, I have computed some of them here. In this case, I don't have any equations, so we don't have any exercise, but I think we can imagine, for example, that the intermediation, let me see here, to go from here to here, for example, these nodes are not important. You never go through these nodes. So that's why the betweenness centrality is 0 here all around in these nodes. We don't need to go, they don't serve as an intermediate. That's the idea. While the central node in the first network is a very important one. His intermediation is the highest. So it has the highest betweenness centrality.
So there's another way of saying it would be that the capacity or the capability of any one particular node to act as a the intermediate one.
That's exactly that. Sometimes we call it the capacity of that node to act as a hub, to act as a bridge, between two different nodes.
Right.
That's exactly that. Yeah. So this is a different way of seeing centrality. So now we have seen three different ways of seeing centrality. One only based on the degree, another one based on the proximity of the network, we call it closeness, and now the betweenness centrality that has more to do with the intermediation or the betweenness. Yeah. And so before the break, I think we can make some experiences with Gaffy. What do you think, Saleha? Maybe?
Yes, sure. We should do that. We have time.
Yeah.
Because
until break,
the break will be starting at 4:20. So we have a half an hour.
Oh, it's not 11:30. Maybe I had a wrong idea. So at what time should we start the break?
It is like 4:20.
4:20. So okay. Thank you. I thought it was at 4. Okay.
No. Because of the shift in the prayer time according to the movement of the sun.
Great. Good. Thank you. So let's use Gephi. I don't know if you are familiar with this software. So Gephi, as I said, is a very easy to install and easy to use software to deal with social network analysis. It's a free software.
Pedro, I tried to. I started downloading it about 1 hour ago, but then it said it may harm your computer.
Oh yeah. I think I know the reason why. Yeah, I think I know the reason why it says that. So yesterday, I'm using a laptop that it is not mine. It's from Statistics Portugal. So I use this one, and it also said that. So beware, because it can harm your computer. And I know why the message is there. It's because you need to install Java. Yeah. So this Gephi software is based on Java. And if you have Java already in your computer, it's not a problem, but otherwise you need to install Java before. So you need to install the Java version 7 or version 8. So I mean, it is the last version of Java. But it gives you a message when you try to install, and you install until the end. But then if you have no Java, so it takes maybe 30 seconds. Once you download the file, then you run the executable file. It takes less than 30 seconds to install everything if your computer is fast. But at the end it says, okay, it's not going to run because you have no Java. Or maybe can say, okay, be aware because it can harm your computer. So it's up to you to install it or not, of course, but you need Java, otherwise it won't run.
And Java is free or Java has to be paid for?
No, Java is completely free. It's from Oracle. Yeah. So this is the homepage of Gephi. So if I click here, I'm going to start downloading Gephi. So it's what's happening now. I'm not going to install it again, of course, but once you click here on this, I think you can see my button on the left side, the left-hand side of the screen at the bottom. Now, if you just click here, you are going to install something. I think I don't have permission, so I'm not going to do this because I need to have a password of administration. But so I'm going to cancel because I've already it is already installed. But then at the end, you need to go to Java. So if you need to go to Java, sometimes I think it's written here somewhere. It says that.
Well, it's all right. We can sort this out later. Yeah.
Okay. So yeah. I think it is here in the installation instructions. Yeah. Okay. It's here. It's exactly here. So in the installation instructions, which is very easy. So I just went reading and then I found this. And it says Gephi is compatible with Java 7 and 8 versions. Download free from here. So just click here and we will download it in less than 1 minute.
Okay.
Okay, and that's it. So then you will have this program. I have already, it's already running in my computer. So this is Gephi. So now you can see a network here, or well, I have different networks running. So it depends on what you want to see. And then I can. So I'm going to start from the scratch, of course, but I'm just showing you how it works, and you can optimizing the way how the network is, is running. So it's pretty interesting the way how it works. So this is a network of, in this case, this is a network of. I think this is a scientific network. I mean, that are papers and authors. So you can see the groups that are interested in the same kind of papers. So I collect this information. This information is also available in the page of this course. Let me stop. So
can you show us the data, Pedro?
Yeah, yes, of course.
Data file?
Yes, I'm going to show it right away. So let me just maybe first introduce Gephi. I need to go back to the slides, and then we will see this example. So Gephi is one of the best known tools for representing and managing networks. So it's we can say that this is a software for network mining. So it's a collaborative free software based on Java. So it's completely free. It says that it has some numerous applications in areas such as biological, health sciences, economics, and so on and so forth. And okay, if you need some help, just go. So there are plenty of files and help. If you just Google Gephi, you will see many things there. So now my suggestion for this practice, so maybe I'm going to do it myself, is to use Gephi to analyze the Karate network, the one that I have already mentioned before. So this is the network. We are going to do this today. This is the network of persons in this club, this Karate club. And then we will represent the network with a graph and optimize the representation using different layouts. And then we will calculate some of the network measures like, the degree, the closeness, the betweenness, and so on and so forth. And then we will export the graph. So the Karate network is one of the networks. I think I have the materials here. Yeah. So this is the materials that are available for you. Karate is here. So the Karate is a file already in Gephi format. So after opening something that you can do by yourself, then you can save and store it as a Gephi file. And the Gephi files have this format, GML. So that's what I'm going to do now. I'm going to open here this character file. So it's very, very easy. So you can see that the number of nodes is 34. So basically in this club, you have 34 members and corresponding to 78 connections or edges. So, you know, people, same person can have more than one connection. So overall you have 78 connections. So that's nothing that you can do more now. Just open and that's it. So suddenly something is being shown in the center of your space. So let me maximize the window. And now, so this is the first exercise to open the network. But now the network is not very easy to understand. So let's choose a layout here and see what we can do with them. For example, let's try expansion. So I have to confess that sometimes I don't distinguish from these different types of layouts. So what I do, and I think that almost everybody does here, is just to try out and see what are the most important ways of representing this information. So I'm going to start with the expansion and then run, for example. So it's expanding the network. So it's for us to see it. Let me try another one. I'm going to try now the force atlas algorithms for, okay. So it's a different way of representing the network. It's too small. So now I'm going to expand it, stop, and choose expansion again. So as I said, there is no typical way of doing this. I confess that sometimes I choose one and some other times I choose a different one. We can also, for example, choose this Fruchterman-Reingold and then expansion again so that it can be bigger. So as you can see, this Fruchterman-Reingold puts your network like a ball. So for small networks, I confess that I rather prefer not to do this. So maybe I'm going back to the Force Atlas again, like this, because the network is small and you can see it better like that. So I'm going to enlarge the network. And so now I have a network. These are the tools that you can use to select some of the nodes. For example, you can select a part of it or grab it, for example, like this. You can select a part of the nodes, and if you want to extract only a part of them. I think it's a little bit difficult to see the links, isn't it? So I'm going to maybe select a different tool. And now, sorry.
Can they be made dark somehow?
Yes, that's what I'm going to do exactly. So I'm going to put, you see what's happening? So I'm putting the links more dark, like that.
Okay.
So now you can do everything here. Yeah, you can change, for example, if you go down, sometimes this box is not open, so I'm going to open it. And now you have this global, so you can change the background color, for example. I'm not going to change it because the white is good, so that you can have a contrast between the network and the background. But you can change, for example, okay, you can do a zoom here, like that, you see? So this is the network. Now you can use the scale for the edges. So the edges are the links. You can even change the color, for example. I can put them, I don't know, blues, for example.
Mm-hmm.
Okay. And for the labels, because we don't know who they are, we can also use labels here and use the fixed. Fixed means that everybody is going to have a label, no matter what we are representing. For example, this is the person number 13, so we don't have names. For a matter of simplification, it's better to have numbers than names. So this is the person number 29, and so on and so forth. So this is the 34. And that's what we can do here. So for a start, this is a network. Of course, now you can export the network like here. So you can have a graph file in the GAFI format, or then you can save it like a PNG file or a SVG or a PDF. But before do that, I'm going to compute some network degrees, the ones that we have been seeing. So you see, some of them are here. For example, we have the network diameter, we have the graph density. So all of these measures are computed at the level of the network. So these are what we call the network overview. So these are the measures available for the network level. So if you compute, for example, let me do it, the average degree, I'm going to run it. So it means that this is the average degree of the network. So overall, you have an average degree of 2.294. So it means that all the persons in this network, in this club, have in average 2.2 connections. That's it. So on average, you have 2.2 connections in this network. That's the average degree. But considering that they may be a weight, I think that there is no weight here. Yeah, there is no weight. If the links were weighted, in that case, the average weighted degree could be different, but it is not different because this network is a binary network. So you have whether you have a link or not. Let's now look at the network diameter. So this is an undirected network. So let's consider first that the network is undirected. And so the network diameter is 5. So the shortest path between the furthest nodes is 5 in this network. Can you see number 5 here? Yeah.
Number 5.
Yes.
Yes, it's here.
Yes. Okay.
Can you see the pointer of my mouse? Yeah.
Yes.
So the graph density, we have computed that before. It's the number of links that exist in the network over all possible links that would exist if everybody was connected to everybody else. So considering that the network is undirected, the density is low. It's not very high. It's about 14%, 0.139. So you have plenty of measures. Now let's take a look at the network. Sorry, at the measures or the metrics at the node level. For example, if you want,
Dr. Pedro, I have a question.
Please.
This 0.139 or 0.14, it means that only 14% of what could have been. Is that right?
That's right. So only that's right, of the could have been. Yeah, among all the possible links in the network, there are only 14% of these connections. For example, if you take a look at 16 or 22, if these persons would connect with all the other persons, in that case, the number of connections would be very high. But that's it. So some of the members of this club only know a pair of them, or only know one, are friends of a particular person, and so that's why the density is too low in this network. And this is typical, as I said. So I think that you asked me before what is good or bad in terms of density, and I answered that in the most part of the real world networks, the networks have low density.
Right.
We're going to talk about that later on. Yeah. And so these are the node overview now. If you want to know, for example, what is the, so unfortunately the types of the network metrics that are computed at the level of the nodes are not the ones that I have introduced. We don't have between the centrality here in Gephi. We don't have closest centrality. We have different centralities, but we can compute them at the level of the network. I'm sorry, at the level of the nodes. So for each node, now you can see what is the clustering coefficient distribution. This is not very far from the closeness centrality. And the same here. But what is good here now is that you can take a look. If you go here, so you see those links here. So let's go to data laboratory. So we are in workspace 14. So it means that I have already opened different workspace in my software. But now let's go to the, so we are in workspace 14. Let's go to the data laboratory. And in the data laboratory, you can see the data. So these are the nodes. We have, I think that we have 34 nodes corresponding to 34 persons in this network. And it computed already these statistics for you. So you have the in degree, the out degree. Of course, the in degree and the out degree is, we don't have it. No, I'm sorry. So it's true because it means that indeed this is a directed network. This is not an undirected network. So it means that also, yeah, that's why the in degree is not the same as the degree. So you can have different measures. Yeah. So the degree is the overall sum between the in degree and the out degree. That's right. Then you have the closeness centrality, the one that we have computed. And we have other kinds of, so you cannot compute it, but it computes it for yourself. You can see it here, the closeness centrality, the one that we have computed before in the slides. And you have the betweenness centrality as well. For example, the highest betweenness, now it's ordered according to it's sorted out according to the betweenness centrality. You can see that the highest betweenness centrality is in the node. Let me confirm if this is true. Yes, it is true now. You can confirm that the node with the highest intermediation, meaning the betweenness centrality, is the node number 1. So maybe the node number 1 is the most important in this club. If you want to make some political action, for example, if you want to say something to someone and so that person can influence the others, you know, this an example of something that maybe we could do in this network is by contacting the node number 1, because the node number 1 is very central in this network. His centrality is 231. I don't know if you can see this number.
Yes. So
okay.
Then this number does not, I mean, its maximum does not have to be 100.
No, that's right. No, we don't have a maximum of it has no range. I mean, it has not to stand between 0 and 100, for example. It's not a percentage. Yeah.
And what is this eigenvector centrality or
eigenvector centrality is a different type of centrality. So we just learned 3 different types: betweenness, closeness, and degree. But there are other types. There are these eigenvector. These are also the harmonic closeness. There is also the where is the other? The harmonic, the clustering centrality. That's another one. So these are slightly different, but all of them measures the same. So the eigenvector has to do with the how many kind of different clusters you have in your network, and based on that, it's a way of optimizing this measure of centrality based on how many hubs you have in the. It computes a kind of an eigenvector, and then that's the eigenvector centrality.
Mm-hmm.
And for example, if you compute the eigenvector centrality, the node number 1 is not the highest because the node number 1 was the one with the highest betweenness centrality. But now the node with the highest eigenvector centrality is the number 34. By the way, the node 1 is the second one with highest eigenvector.
Mm-hmm.
So they are competing for having the maximum centrality, but that's why sometimes these measures are not very different. But if you want to take a deeper look on the type of centrality measure, they are different. If you look at the betweenness, for example, the highest one is going to be 1, the node number 1, and then the second one is 34. But if you compute the eigenvector, is the other way around. The highest is the 34, and the second one is going to be the node number 1. So it depends on what kinds of thing you are measuring.
Right.
So in this data laboratory, you can see everything about your data, and you can export it to Excel, for example, or then you can also import from Excel. So maybe just to finish this example, let me go back to the workspace and to the overview. And let's do something that I have not introduced for a matter of time limitation, which is the computation of the communities. So for computing communities, where are them? They are here. We use the measure of modularity. Yes,
Pedro. I think you have computed various measures, of centrality, closeness, betweenness for the undirected, I believe. But this data is for the directed, I believe.
Yes, you are right. I can compute them again. Yes, you are completely right. So let me do it again. Now it's giving the degree distribution, the in degree and the out degree. So in this case, there is not a problem. But for the average degree, you also have the degree, the in degree and the out degree. Okay. So I think that the problem is here in the graph density. So now I'm going to say that the network is directed. And now it's computed as a directed graph, and also the same thing for the diameter. I'm not going to normalize centralities. And now it's 3, yeah. So it changed. Now it's not as 5 as it was before. If we consider that the network is directed, it means that you cannot go back. So you have to follow a direction. And so that's why the network diameter is 3. And also here in the clustering coefficient, okay, and the eigenvector centrality.
Is it good to have a bigger diameter or a smaller diameter?
What value are you referring to?
I mean, in general, is it the diameter should be bigger or smaller?
It depends, of course. What is the importance of the diameter? Imagine, for example, that you are working in a telecom company. We can do a social network analysis of phone calls, because A makes a phone call to B, then A can also make a phone call to C, but C makes a phone call to D or to A. So you can now imagine the huge amount of links, of connections that are established whenever you make a phone call. And this is a directed network, because you have a start, the one that starts the connection, because it starts the phone call, and then the receptor of it. So based on this, for example, you can compute the diameter of the network and see in what extent one company has a wider range than another different company, for example. And who says that, for example, I don't know why I have remembered, it just came to my mind, this example of the telecom company, but you can, for example, imagine a different example of a friendship relationship in your university, and see in what extent they are, one is bigger than, for example, in the classroom, one friendship diameter relationship network is bigger than the other. So I wouldn't say that there is a kind of a limit for the diameter, but these kind of measures are important for you to see how large a network is. That's maybe the reason, the most important reason why you need
Right.
to look at diameter.
Okay, thank you.
Okay, so now to finish this example, let me use the modularity. So the modularity is going to be used to compute communities. So it has found 4 communities so far. You see, you have the community 0, the community 1, the community 2, and the community 3, and we have 11 nodes in community 0. You have 5 nodes in community 1, 4 nodes in community 2, and 14 nodes in community 3. So it means that we might have 34 nodes overall. And this is the distribution of the, so this the algorithm that has been used here is the modularity algorithm. It's these are the authors. And when you do that, sorry, something happened here. Okay, I'd like to to change it a little bit, and I'm having some problems, but it's not a problem. Now I'm going to represent these values in colors because we didn't see anything. We just compute the modularity, but okay, so what is the result of it? Of course, we can take a look at the data laboratory. And in the data laboratory, you can see for all the nodes in the network, the 34 nodes, who are the groups to where they belong. For example, the nodes 1 to 4, they belong to the class 0. Then 5 to 8, you see, to 7, they belong to 1 and 0 and 3. So it's like a clustering. We are doing a kind of a clustering, but instead of clustering, this is the modularity. So we are computing the communities based on the distance of the groups in this network. So what I'm going to do now, sorry, I need to enlarge a little bit. So, and maybe decrease the number of the text. And now I'm going to represent the nodes, the partition, by using this where is it? I should find here so the modularity. Oh, of course it was there, but I need to go down a little bit. Yeah. Okay, so it is here. So now I can represent everything because I've computed all these network metrics. So you can go from your left-hand side and see what kind of representation you can do. So you can represent the degree or the in degree, the out degree, the between the centrality. I'm going to choose maybe the modularity. So it's a partition measure, not a ranking one. So here it is, modularity. So you have 4 colors. I'm going to apply them. And now, so now this is a matter of aesthetics. So if you want to, for example, extract the numbers of the nodes and then try to increase it, or then you can put the numbers because they are important for you to know who the persons are, and for example, change them. There are different ways of doing this. For example, now the colors of the nodes are also representing the communities. So you have 4 communities. Now you know this. Do you remember the node 34? I need to enlarge a little bit the graph. I think you can see now this area here. So this is the area where the node 34 is. So 34 is one of the members of this club. It was a central, very, very highly central one. And indeed, all the community of the node 34 is composed of the other elements of the same community. For example, all these are purple. So this is the community number 3, as you can see, containing about 41% of all the elements in the network. Then you have the community, a different community here, the community of the oranges that represents 14% of the old elements, and then you have the greens, community of the class 0, and the blues, community number 2, a very small one. So this is good because now we can export this graph, for example. I have to do something here because before exporting, you need to go to the, this is a very important, very important setting. You need to go to the preview settings. And for example, inform that you want to show labels. And I think because sometimes it's very difficult, you have to, you know, to try and to repeat sometimes because it's not very easy to understand these options. And I think that you should not choose the proportional size. I'm not sure, so I'm going to do this again. Now I'm going to export. And sometimes I use the PDF. Let me call, I don't know, today, for example. And let me take a look at it. Okay, oh. This is a network, but it came with no labels, so we don't know exactly. So you can see the colors. So you remember this is the node 34, but it should be there. So something went wrong, but this is the output of the network. So I need to go there, maybe into, it should be there, show labels. Sometimes I also need to go to the preview settings here. So, but it's there, it should be there. Oh, I think I know why they didn't show. Because maybe the graph, yeah, sorry, this. I think that the graph should have
Dr. Pedro, it's
yes,
time for the break.
Okay,
like,
of course. I think it's better to stop here. I'm sorry, but I think
okay.
Yeah, we have just finished the example. Now this is a matter of, you know, aesthetics and try to optimize this graph here. So this is a matter of putting the labels there. But so I'm going to stop sharing my screen.
Right.
And we can do a break now. Yeah.
Right, ladies and gentlemen, it is 4:24 p.m. on my laptop. So we'll meet at 4:34 p.m. Thank you.
Thank you.
Okay, Bismillahirrahmanirrahim. Ladies and gentlemen, we are starting the second part of the workshop after the break. So let me share my screen. Okay, I think you can see my screen. Is that right?
Yes.
Jawad sir? Okay, all right. Yes. So we had one moment. Let me just try to. Okay, so after this presentation, we had this short break. And now I want to spend a few minutes talking about the upcoming conference and post-conference workshop. You've seen this flyer. Many of you, I'm sure, have seen this flyer a number of times. I just want to highlight some of the things today. This is the conference program. So we begin at 8:45 a.m. Pakistan time. We have an invited talk by Mr. Sajid Rasool, who's the Director General of the Bureau of Statistics, Punjab, right here in Lahore, in Pakistan. We have an invited talk by Dr. Amjad Javed Sandhu, who is Census Commissioner at the Pakistan Bureau of Statistics. Then we have a short break. After that, we have contributed papers, parallel sessions in simultaneous virtual rooms. And then we have about 20 minutes for talking about IASS, the International Association of Survey Statisticians, and also about PISTAR and ISOS, along with some networking between the participants of the conference. At 11:25 a.m. Pakistan time, we have an invited talk by Dr. Daljit Singh Virk from the United Kingdom, who is very much here with us today also in this workshop. And after that, we have an invited talk by Professor Hanif Mia, who is my teacher and also who's the president of PISTAR as well as of ISOS at this point in time. At 12:20 Pakistan time, we have the poster session, the display and the verbal presentation regarding posters. And then at 12:45, we have the second contributed papers parallel session. And then we have another session for networking and for talking about IASS, PISTAR, and ISOS. After that, we have an invited talk by Dr. I think this is Mr. Muhammad Sarwar Gondal from the Pakistan Bureau of Statistics, Islamabad. He will be talking about the first ever upcoming digital census of Pakistan. And then we have an invited paper session by Professor Yai Kwang King from the United States of America. And along with himself, he will have one colleague from Norway and another one from China in this particular session. And after this, we have, now I have a problem because I have this black bar on top of that thing. Please allow me to stop sharing for a second, I'll say it. We will have the keynote address by Professor Monica Pretesi, who's the president of the International Association of Survey Statisticians. They are that's the association who are sponsoring this conference and post-conference workshop. And the closing session is from 4:30 to 5 p.m. Pakistan time, in which we have a virtual prize and certificate distribution ceremony. I will now try to share the screen one more time. I hope you can see my screen again. Can you see my screen?
Yes.
Yes.
Okay. So after that, we have these important dates. So we have been extending the dates again and again and again and again because we want the maximum number of people to join. So if you want your paper to be included in the best poster competition, you still have 4 days for the submission of the abstract, and the acceptance will be given, or non-acceptance, I hope not, on the second day, next day only, because we don't have much time, so we'll do it immediately. And then we have the full-length paper submission for this 4 more days for that, because we have been saying it for so many days, so we are hoping that people can still do it. And then if somebody misses this particular deadline, then still they can submit their abstract by the 5th of March, and then acceptance on the second day, next day, if it is of that quality that we need, and then the full length paper submission by the 9th of March. As far as posters are concerned, please submit them by the 5th of March if you want them to be included, because obviously the panel of international judges from all the different various countries of the world, they also need some time for evaluating them. So please give them by the 5th of March. Otherwise, still, if you miss that deadline, you can still submit them till the 9th of March. Early bird registration is the 25th of February, and the regular is on the 12th of March. Even on that day, you can register. And if you've missed a bit of it, you can attend the rest of it. The Best Paper Award is an incentive that we are giving, and the Best Poster Prize is another incentive that we're giving. And we have already got papers, the abstracts to me seem to be of high quality, but we want more. We want more people, and we want them from different countries of the world. Authors of selected papers will be invited to submit further refined versions to the Pakistan Journal of Statistics or to the Journal of ISOS. And then 1 year free membership of PISTAR. All those who are registering for this conference will be given 1 year free membership. The conference registration fee is absolute minimum, because the ISS also wanted that, this knowledge sharing should be, it should be like this, that those people who are generally not getting such opportunities often, they should also be getting this knowledge. So then on the next day, I must talk about this workshop too. This is the Center for Remote Sensing at the University of the Punjab, right here in Lahore in Pakistan. And these are the people who will be doing it. And so they'll be talking about the working principles of satellite remote sensing and image processing. And then next session will be on the remote sensing data applications in field-based surveys. And the last session will be on the role of GIS, the Geographical Information Systems, in census mapping and demographic statistics. And again, the registration fee is the bare minimum. So you can scan on this QR code. And if there are problems, you can talk to Dr. Syed Wasim Abbas or Mr. Muhammad Iftikhar. But otherwise, if you're any one of you who are attending this now, if you're interested, you can write your email address right here in the chat so that Dr. Wasim can pick it up, or you can call him. This was the announcement. Next, back to the workshop and over to Dr. Pedro Campos. So I will now escape and I will stop sharing. Over to you, Pedro.
Thank you, Salia. Can you please remind me how much time do we have left?
Okay, I will do that by looking at the plan. And in the plan, it says that further presentation you would do till, you see, if there's no separate question answer session, then you can go on till 5:15, meaning like half an hour. But also, if there is not much verbal feedback from participants, then you can go on till 5:35, meaning that you have 50 minutes, 50.
Okay.
In that case, if you need it, then I can request the participants to give the feedback in the chat. But although we do want some people to also say something. So how much time do you think you would need?
I think maybe 30 minutes will be enough. And then after that,
okay.
Until 5:15, yeah. And then if there are some questions, we can spend the rest, I don't know, until when, trying to
5:35. 5:35.
Yeah, in case people want to chat or something. Okay.
Yes. Okay. Thank you.
Thank you. So PISTAR is completely having lots of success, as you can see, with lots of initiatives. So congratulations for all these initiatives.
Thank you.
It's very good, very good. It's a very good benchmark, a good case of success that we should follow also in other places.
And Dr. Pedro, I must thank you for accepting the position of being country coordinator for Portugal. We are honored.
It's a pleasure, as you know, yeah, for me.
You're so busy, such a busy person, and so much to do. And you have also honored us by doing this.
Well, I hope that I can contribute, even with a small amount of time, to trying to explore new directions, new initiatives, and to help you as I can, of course. Thank you.
Thank you.
So I'm going to share my screen again. And so we were exactly in that part of GEFI. So I'm not going to enter in detail in much other things. So Let me go where we were before. So this was the place. Yeah. So we have done this exercise 2. So this is a screenshot of Gephi. I saw that some of you have already installed it. So it seems that maybe it's not very I think it's very fast, but as I said, you need to have Java installed first. So please just follow the instructions there. It's a very small link that you need to follow, and then you can install Java in case it does not run, and then it will run. And the installation is very, very fast. So basically, what I have been using in Gephi was this open button here in the file menu. Then you have also the network overview and the node overview, and of course the main screen with the networks. In this case, I have already done some configuration, so it's a matter of trying to look at it and try to optimize the statics of the network. And then on your left hand side, also below the file menu, you have also some things that you can do, like for example computing the modularity, or at least representing the modularity. And below it was the layout way of showing the network. So these are, I would say, the basic things that you can do. Of course, you have this data laboratory here, where you can see the data itself. We are going to do this again with another example. And whenever you do the work, use the workspace. So in this case, I was using the workspace 3. So if you go to the data laboratory, you will see the data. If you look at the graph, if you look at the overview, you usually see the graph, and in this part of the program.
Dr. Pedro.
Yes, please.
Sorry, can I ask a question?
Yes, please.
Sorry, is that any way in the Gephi to separate the graph by clustering, by clusters, majorities automatically? It's a very important problem in the graph sentencing. So is that possible in the Gephi or not?
When you say to separate in clusters, you mean that, for example, each node belongs to a different group?
Yeah, yes.
Yes, I think so. So let me show you the Gephi here. So we were in workspace 3 or 4. Or, I think it was the last one. It was the 13. Yeah, we were here maybe. So if you go to data laboratory, I cannot see the graph now, maybe because it's very, oh, I think it's very, I think it's somewhere there, but I cannot see it. Okay, so I'm not going to take the time to do it, but I'm going to show you the data laboratory. So if you go to the data laboratory, and if you go here to the modularity, I'm going to click on this last column here, you see? So,
okay, yeah.
So if you export this file here, if you export the table into Excel, for example, you can separate the nodes. Here you have the node 1, the node 10, the node 11, see, and according to the group where they belong. Was that your question, Alizare?
No, my question is that how we can separate them in the graph.
Okay.
The chart of the graph. Yeah.
Now I see. Thank you. Now I see the point. So let me go back to Gephi.
There are a lot of structures to showing the graph, but most of them cannot separate the clusters each other's between. So
yeah, I think I understand your question. So let me see if I can do this. So now I have another example of the same problem. So this is the chart, and I think, I'm not sure, when you say separate is only visually is
exactly visually.
Okay, yeah. Okay. I think the way to do that, well, it's not perfect. So I was going to do something that I think I've already done before. So it's like doing this. but this is not exactly what you wanted, I think, because this does not, extract everything. Yeah, this does only take one of the nodes, or for example, this the node 34 or the node number. This was the node the 34. Now I'm going to take node number 1. Yeah, but this is not the same. Well, to be honest, I don't know what to do that automatically to separate. I don't even know if it is possible.
If the problem is grow up when you have very huge network, it's very hard.
I'm sorry, I could not follow you.
When you, if the problem is grow up when you have very huge graph, a huge network graph. So when you want to make the cluster, manually, is very hard. But
you are completely right. In this case, it's not a problem, but in the cases where you have a very, very huge graph, it makes no sense. Yeah, of course, you need to do this, but I don't think it is possible in Gephi. So Gephi, because it's a very, visual with a very good graphical user interface, sometimes it's limited. These are the kinds of things that I'm sure that you can do in R. Maybe this is something that we can do in R, but we need to program it. But
yes,
well, I'm not sure if it is possible, of course, to do it in Gephi. I needed to confirm, but if you don't mind, I can take this note, and after the course, meaning, for example, during next week, I can just look for that, if it is possible to separate.
Okay. That will be nice.
Thank you so much.
Okay, no, you're very. This is also good for me to learn, to separate the groups.
Pedro, I also have a query. I also requested you before. I want to see the input file. How do you organize your data, in which way you put the parameters, and what are the data inputs?
Okay, thank you. Yeah, okay. In my next example, because I think this is most important, that's what I'm going to do. I'm going to open an input file using Excel and do it there, because the input file, you can also you can also see it here. The input file it's exactly this one. Sorry, I need to go first here. Yeah, so this is the input file. You have Okay, so this is the input file. You have two types of the input files. You have the nodes, which only contains the IDs of the nodes, the IDs and the labels. In this case, they are the same, and all this information that I've showed before. And then you have the edges. Edges meaning the links. So all of this you can import directly from Excel. But this was already there, so it was not up to me to import this data. So I have used the data set that was already available in Gephi. So what I'm going to do next is do it from the scratch. So I'm going to import the data from an Excel file and try to deal with it with Gephi. So I think I'm going to try to answer your question. Okay.
Thank you. Yeah, that will be good.
Okay. So this is the exercise number 2. So it's going to be the following. Yeah. Okay. So this is the exercise number 3. Now we have a bipartite 2-mode network. So we are going to load the nodes and the edges separately. So this is not a very easy task. So I'm going to try to do my best. But as you can see, it's going to be very easy. So it's so I'm going to use a file. I don't know if I have the source of this source. I mean where did I extract this data from? It's about scientific collaborations, the authorship. So you have authors that produce papers together, and then you have the topics of the papers. So that's why this is a bipartite, because you have two types of different nodes, the authors in one side, and the topics or the themes or the numbers or the names of the papers on the other hand. And that's it. And then we are going to, so I'm going to do everything from the scratch now. So let me go to Excel first. Where is my Excel file? I think I can go here first. Okay, so I'm going to start with the nodes. So all this information is available in that the folder that I shared with you. So this is a CSV file. It's not very easy to read, so let me parse the data to something more readable so that you can understand it, and so is me. So do I. Okay. So this is the information about the nodes. So let me do something like that so that you understand. So these are the authors. This is their ID. So how many authors do we have? I think we have many of them. Yeah, we have 622. So they are not a lot, but they are much more than the 34 of the previous network. Then you have the name of the person. So these are people that collaborate. These are authors, scientific authors. I think that they are scientific authors. I'm not sure. I don't know if they are authors of something or if they produce papers, but they collaborate in a certain extent. So I'm not the source of this network. I can give you the references later on. So these are the person. And then let me go there. Yeah, until 353, we have persons. Then starting in 354, the new nodes are not persons anymore. They are topics. For example, the topic 353 is virtual cities and digital histories. And this is do birds of a feather really flock together, or how to choose test samples for authorship attribution, and so on and so forth. So these are maybe books or scientific papers, things like that. Network, literature and culture, cinematics, digital. So these are topics, as you can see, starting from here. And from this way to the top, these are names of authors. So you have two different types of nodes. So everything is in Excel or in a spreadsheet. Then you have some other information, like, for example, you have two types of the nodes, as I said. So the individuals. And then starting in 350 something, you will start with sessions. Can be movies also, movies or sessions or books. And then what else do we have? Yeah, we also have some information about modularity already computed. So maybe we have downloaded the file already here. So this is the information about the nodes. Now I'm going to show you the information about the edges. Where is the information about the edges? Okay, it's here. So the information is about the edges is much simpler. What we have is basically an arc list with a source and a target. So for example, here it means that author number 1 has read or has written or has attended to session 353. So it depends on if it is a book or a paper or something, some session of cinema, for example. And so it depends on what we are talking about. So it can be authorship or it can be anything else. And the person or that person number 1 also attended or has written session number 1416. So, and this is what we have. So now I'm going to download this data or upload this data to Gephi. I don't know if I'm going too fast, but please tell me if I'm going right with that. So
I think it's all right.
Okay.
Is it
good?
Yeah.
So maybe it's more important to show you my slides because everything is there. So first, load the DH11 underscore nodes and DH11 underscore edges. These are the two files. I'm going to load the files to Gephi. And please note that after selecting the first file, in the data laboratory, remind to select the nodes. So I'm going to start with edges first. I think it's the order is not important, but I'm going to start with the edges. So let me do it now here, open. So I'm going to start with the edges. Okay. So it immediately understands that, okay, so the file is being well read. Next. And finished. I think it's, so it's 621 nodes. I think it's more or less what we have. So it should be exactly what we had. So the graph is directed. Yeah, that's right. In this case, it's right directed. And so it is. Now we are in the workspace 15. So these are the edges. And now, so you see that here we have two separators, two different entries, nodes and edges. So now I'm going to click on nodes. And I am going to import the other spreadsheet with nodes. It was the previous one, the one that we have seen firstly. And then pay attention, please, to this point. Before I go on, I'm going to click here on this radio button, informing the software that I intend to append this file to the existing workplace. It's not going to be for a new workplace. It's going to be appended to the existing workspace. So that's what I wanted to do. Now I have a node list, a node with the identification of the nodes. So this is node number 1. So they are not sorted. I should maybe use a different sort, but that's not a problem because the sort, it's like a text sort, like a 1, 10, 100, but that's not a problem. Everybody's here. And then these are the edges. So, and now it makes sense, you see, now because everything now is structured, because now the software understands that the nodes corresponds to, for example, node number 1 corresponds to this person, Robert C. Allen. And then we have the target 353 that has a correspondence with the source. These are two nodes, but there are different nodes, different types of nodes. So we have a correspondence between one mode and another mode. So that's why this is a two-mode networks. So in this example, that's the example that we have. And that's it. Now, if you want to go back to the data, you see the data is here already plotted. Of course, this is very difficult to understand. Maybe because we have, like Ali Reza said before, this is a huge network. And because we have a huge network, now it's becoming more difficult to look at it. So what I'm going to choose is maybe the right layout. I don't know what should I choose. Maybe this force atlas and run. So the software is trying to optimize the structure of the network so that you can see it better. But okay, it contains 621 nodes with links with many different nodes. The density is not huge, as you can see. So there are not many nodes connected, but still it's very complicated. It's very difficult to understand the nodes, the network. So I'm going to stop. It still haven't stopped. So it's, as you can see in my right-hand side, bottom of the screen is still running. So I can stop it when I want. Oops. Let me cancel. Okay, so I stop it now. So I have, as you can see, I can enlarge my.
Dr. Pedro,
yes?
this is all this is very fascinating, but I want to ask you, in the real world, all these huge organizations who are doing this kind of work, then how do they actually, I mean, get something out of it? If it is so complicated, how do they get meaning out of it?
Yes, of course. The problem here, so the network science has to do with different things. One of them is representing the data by using this kind of graphs. And sometimes it's difficult by using the graphs, just by looking at the graphs to extract some kind of knowledge. But then you have the other way around, the other possibility, which is using statistics. And then for the statistics, we have this kind of network measures, you know, the network measures overview and the node overview. And based on this, maybe you can then extract some important information. So that's what I wanted to say. So that's not only visual. You should also complement the visual information with the statistical information from the network metrics that will help you to understand better the data.
Right. Mm-hmm.
Now, for example, I'm going to run modularity because I think that modularity will help us to see. Well, it's lots of classes. It's going to be difficult to find, but it means that because the number of is like in cluster analysis. Sometimes we don't know initially how many clusters we are going to have. So it means that it seems that we are going to have lots of clusters. And now I'm going to represent those clusters with different colors. I think we have more than 50 clusters different.
Oh,
okay.
I see.
So here they are. You can see them here. So this is a problem now because we don't know exactly who they are, but of course I can write them here. But once I write, so it means that we have different clusters, which is good. Different, different communities. We don't call them clusters, which is, although it's almost the same thing. For example, these are people that usually are associated with the same kind of sessions or books or whatever. And the same happens to the others. And let me write the labels here. Now,
can we actually now identify each and every single person?
Yes, we can. I'm going to do, I'm trying to do that, but it's going to be very difficult because prepare yourself to see something that is going to be almost impossible to read. Okay, see? Yeah, because
wow.
the names of the things are very, very long. I can just shorten the names, and I of course we can increase by doing a zoom. For example, I can look at a part of my network and try to, let me not here, yeah, here. For example,
These are the titles of books.
Yeah, for example, this is a John, I don't know if you can read this name here, John something. Is connected to the dramatically approach to something. It means that it's a kind of a documentary or book or movie. I don't know. It's a authorship, and this person is attached to this one. And also, okay, if you click on that, you can also see that Brown University is also connected to him. So, of course, for simple parts of the network, you can take a look at them. And this is going to be important for you to understand how these interactions between the nodes can work. But of course, if you want to take a look at the old network, like the one I'm going to do now, of course, it's going to be more difficult. So it's important to make these representations, but don't forget that these representations will help you if the networks are smaller. Of course, if they are big, they can also help you. But in that case, you must do what I'm doing now. It's make a focus on the network and try to understand what is exactly there. For example, I can take this one here. So this is a node without connections, for example. In this case, this node has connections. So you can take a look and see, but for more, let's say, overall measures, in that case, you should run those measures there and try to extract some information about the network. And so that's it. So I think it's important to have a notion of the network. For example, in this case, we have plenty of groups. And of course, we can take a deeper look and see how many groups we have. I think that we have something like 50 something groups, or maybe more than that. Let me see. Yeah, I think it's something like 56 or something groups. I can just confirm that. Yeah, we have 60 groups. So there are plenty of groups that are not connected together. That's why we have 60 different groups in this network. Now, if you want to look at it, you can just export it and save it like we have done before. Okay, so so this is an example of a real network that we can take a look and take some insights from that, do what we call network mining to the network.
Is there any way of merging these groups? Some of them.
Yes, of course. Yeah. Now we are entering different steps. So of course, now we can combine like we do in clusters. For example, all this information about the groups is here in the data laboratory. So if you go to the nodes, yeah. So you see the modularity class. So for each in single ID corresponding to a person or a session, or, I mean, a book or anything else, you have the modularity class. So you can, for example, see that, for example, this person here belongs to the class 27. This is not a person, this is maybe a book, I don't know, let me see. The tutor's story is a case study of mixed authorship. So this is maybe a book or a movie, modes of composition in 3 authors, I don't know. The New York University. So some of them are persons, some of them are authors, and they belong to different classes. Of course, we can merge them, but in order to merge them, we should be aware of what are maybe the most, and this is another step of analysis. What kind of things can we do, or what kind of groups should we merge before we do the merge? But we can do this, of course. We have the data in Excel, so we are able now to do everything.
So, Dr. Pedro, in what kind of, where does all this apply and help more? In scientific investigations, medical investigations,
that's right,
business?
I can show you plenty of examples where and that's maybe my last slides, some applications of social network analysis. So this is the same network that I was showing before. Let me say something now about this. Before going to the application slides, let me just say that there are different types of networks. So it has to do with that question that you, Salah, asked in the beginning, if what is preferable if the density is low or high. So I would say that most part of the networks are typical from a specific type of distribution. And let me start with the random networks. So in random networks, they are just random. It means that the probability of having a contact is random. So this is not what happens in real world. Random networks are based on random links, and this is not what happens. What happens in the real world, in most part of the networks, are scale-free networks. So Laszlo Barabasi is a Hungarian researcher in network mining. He has shown that networks are not formed randomly. I mean, real world networks, those that are, for example, those authorship networks or health networks and so on and so forth, they are not formed randomly, but there is a kind of an order in the dynamics of the network structure. And the name of this order, Laszlo Barabasi called the rich gets richer. You see, so it means that the biggest nodes, biggest nodes because they have more links in that sense, they are more central in the network, they become more central ever and ever in the dynamics of the network. In other words, we can say that the more links the node has, the more chances it has to create new links. This is a very interesting property of the networks, of the real networks. And they call this property, this characteristic, the preferential attachment. And this kind of networks are called scale-free, because let me give. I don't have a graph for this. I could maybe find one in Google now, but I don't have time for that. So let me just say you. I think you can imagine this very easily. Let me put things again in this sense. So let me think about people like Cristiano Ronaldo or other football players or actresses or actors that are very popular, and for who the number of links is very high. For example, in Facebook. And I am not very popular. So compared to Cristiano Ronaldo, my degree is very low. So what these authors, what this author Laszlo Barabasi has found is that there are many people like me, and there are few people like Cristiano Ronaldo. In other words, the distribution of the degree is like an exponential, negative exponential distribution. I think you can realize this in your mind, can't you? So the number of the distribution of the degrees, meaning that the most part of the people have low connectivity.
Right.
It has, okay, and
yes.
there are few people with very high connectivity. So that's right. Why we call this a scale-free network. So basically that's it. And let me show you what is the preferential attachment.
But I'm sorry, I did not, I mean, I understood the exponential, but I did not understand why it's called scale-free.
Yeah, scale-free is because it has no scale. Scale means that, it tends to zero. A scale-free network is a network with that has no mean, right? I think that this is the notion of scale. It can help me now because I'm not sure about this. I think that the scale-free network is a network with a scale-free distribution is a distribution, a statistical distribution with no mean. You cannot compute the average. It tends to be something, but you cannot compute it because it never reaches the zero, I think.
Okay, I'm not sure, but we can look at it.
I'm also not sure about this definition, this name, scale-free, okay. But that's the name that they give it. So let me. I think I still have time to do this. It's not very complicated. Let me just look for scale-free distribution, and let me show an image of that. Okay, so this is a scale-free net. Okay, so this is a scale-free net distribution. I think you can see my screen, right? So this is the number of connections. So the most, this is the number of people having those connections. So the most part of people have low connections. And as long as you increase the number of connections, the number of people having these connections are very, very low. So this is the scale-free network. This is the scale-free distribution, like this. It's kind of an exponential negative. And then you have the random network with the different, we are plotting the distribution of the degree. So, sorry, for the distribution of the degree, the random network has a different plot. Okay, so let me, sorry. And let me go back to the slides. So,
thank you.
No, you are welcome, Salaya. So we are almost finishing. So the random networks and the scale-free networks. For example, this is an example on your left-hand side of a random network. And you can see that everything is connected, but maybe not everything. And the kind of links, the degree is a little bit random. So you don't have, there is a probability, maybe a constant probability of connections, but this is not what happens in the real world. In real world, what happens is what you have in your right-hand side. This is what we have, this is what we call the scale-free network. So meaning that, for example, some of the nodes have lots of connections, like the node number 2, so the degree is very high in 2 or 6, or even with a little bit less than that, but even 5. But then for all the other nodes, the degree is like one, because there is only one link. So this is what happens in the real world. We have many people with low connections and few people with very high connections. Okay. Then there is also the concept of small worlds, which is a type of network in which most of the connections are established between the closest nodes. And this is interesting to see, for example, that if you just imagine one person on the other side of the world, sometimes we think that it may be impossible to reach that person because you don't know anyone that knows that person, that knows another person, that until you reach that person. And basically, what some scientists have found out is that maybe you can find this person in less than 6 degrees. So it's very interesting that if you think about one person in the world, you can reach this person with a distance. You remember the distance between nodes with less than 6. So the average distance between all the people in the world is 6. And this is the concept of a small world, which is also studied in social network analysis. So this is my last slide, the types of networks. And I think it's pretty much interesting for you to see what happens in the real world. So basically, in one extreme, we have the regular networks that are very, I would say, theoretical. They don't exist, maybe only in theoretical worlds, or maybe they can exist in some kinds of human networks with very little heterogeneity. So all the degrees have the same, all the nodes have the same degree. So the distribution of nodes is more or less constant. Then in the other side, what you have is the random network. Random means that it's random, so the connectivity is made at random. Then in the other extreme, you have the so-called scale-free networks with high modularity, high heterogeneity. And then you have the networks with high modularity, low heterogeneity, and high randomness. So this is a graph. I find it very useful to see what types of networks you can have in the world. And so I'm sorry, this was not my last slide. Now I have 2 examples to finish. And so, for example, this is, I'm sorry, some of it is written in Portuguese. So this is an example with real data, because Saleha, you asked about real applications of this. So this is a work that we are trying to publish now. It has been made by a former master school student of mine, and she used the trade network, you know, the foreign trade. We're talking about exports and imports in 4 different types of layers. Now we are talking about layers, so we don't have only the same layer because we are dealing with different types of products. For example, high IT products like computers, technology. Then we have medium high IT products, then mid and low IT and low IT. For example, if you're talking about food or exports of animals, this is for sure low IT. So, and now you can make networks of countries. You know, so these are countries, these nodes, they represent countries because we are dealing with foreign trade. And this is what we have done. We have computed the trade relations between the European countries and also between them and some countries with the rest of the world. So, so we have made a plot of the exports by category of foods, and we try to find out communities based on these different 4 types of layers. And this is important so that you can structure the world in terms of foreign trade. Of course, this is a theoretical model, but this is important for you to understand how economics evolve. What is the economic dynamics of the world? And what's good of that is that we have compared 3 different periods of time. So you can see how the foreign trade is evolving in terms of the dynamics of the interactions between the countries in the networks in 3 different periods. I think it was in 2007, 2012 and 2017, I think, the latest data. This is another example now in the health sciences, where you also have multi-layer networks of proteins that you can find in different parts of the body. For example, in the breast, in oral, in ovarian, in cervical, in lung, in colon, and prostate. And this has to do with the cancer types. And now you can make the networks of these proteins. Of course, this is a more biological or chemical process that I cannot follow, but this has been an application of the networks in different types of connections of proteins in different parts of the body. So that's why they are called multi-layer networks. Another possible application, and now for link prediction, is, for example, the product recommendation. This is very used, for example, in Amazon or in other websites where you have e-commerce. This is made in two different steps. For example, in the first step, you have two-mode networks where you have users and products. For example, the users are the square blue nodes and the products are these purple or pink circles. So it means that a user buys a product, so that then you have a two-mode networks of users and products. And then what you want to do is to recommend a new user a product based on the other buys, the other products that have been sold by the same company. So what we do is, well, this technique has been applied also by a student of mine. She has applied a structure where, for example, she has a notion of the a sequence of products and users, and she could predict what the next product is going to be, or what product that person, that new buyer can buy if you recommend it. So this is another thing that you can do by using social network analysis, this network mining process, and that you can, you have the two-mode networks, then you can project them. Of course, this is more complicated because now you are doing sequence of nodes, but based on this sequence, for example, and using kernel graphs, now you can make a prediction of the new links. And so that's it. I just finished my slides. I don't know what I can say
thank
else.
You very much. Thank you very much, Dr. Pedro. This has been amazing. So now I want to ask if there's any question that you would like to do. We can have a few minutes for the question answer. Anyone?
Pedro, this is
Yes.
Abdul Salam.
Yes, please.
Well, you give so many examples and extremely very useful examples. Like I am interested in the trade example, right? You give the example of trade,
What example? Sorry, I didn't understand. What example?
Trade.
Yeah.
Okay. Yeah.
You have given the example of trade data, right?
Right.
Well, I'm interested to know what additional area, what other areas of economics can be used. How the applications can be made through network mining. And I would appreciate if you can recommend a textbook showing the applications of network mining with the real life data, so that would be useful for us.
Okay, thank you. It's a very good question. So I have a friend that says that a colleague from the university that uses to work on this application of network mining to economics and management sciences, and he used to say that all data can be transformed in network data. So basically that's the idea. So maybe you can invent problems, but just by linking. Sometimes it's not very difficult to do that. Of course, naturally, the data that are mostly suitable for network are those that can be naturally where you can find naturally the links and the nodes, for example, like those of external trade because the nodes are the countries and the links are the relationships of the external trade. But the other example that I gave you, that I gave here, is the problem of the recommender of the new products. So basically, you don't have any kind of network there. But now you can invent a network, since you can say that a person buys a product, and if the person buys a product, there is a link between both. And then you can combine all the products that have been bought by the same persons, and then you have a network of products or a network of persons by how can you say, projecting the network, the two-mode network into a one-mode network of persons or products. And by doing this, you can now start doing link prediction. Okay, so these are the two applications that I just mentioned before, the product recommendation and the external network. But there are many others, just if you can imagine. For example, people in finance, for example. So I work in the School of Economics, so I'm maybe more keen to this kind of areas. But for example, in finance, I know many people that what they do is that just collect information about portfolios. You know, portfolios. So you can invest in this kind of asset or in another asset. So you can build a network of portfolios, like in products and users and products. So you can have investors and assets or stocks. I don't know what kind of financial products you can imagine. So the same problem can be applied to finance. So networks are indeed, I would say, a huge topic where almost everything could fit. Just imagine the problem, and I think I can help you changing this problem into a network problem.
And there is a supplementary question. I have it, a supplementary question. Pedro, you mentioned, two type of, analysis in data mining. One was the supervisory learning, other was unsupervised, right? Well, I am more into supervisory for the purpose of projection and forecasting, of course. So in data mining, can we do all those forecasting and projection as far as the data mining is concerned, and network mining is concerned? Can we replicate all the models, or there are some additional models?
Yeah, so we have studied different the data. This is data mining after all, because you are trying to extract information from the data. The only difference is that this data is very complex. So network is complex data. But I think that your question is about, can we do supervised and unsupervised learning in the network mining? Of course we can. For example, the community detection, the application of this modularity algorithm that I didn't show the algorithm, so but you can just find it. It's an algorithm that structures the network into groups, like in the clustering algorithm. This is an unsupervised one. So we can say that in terms of network mining or data mining, the finding of communities in a network is an unsupervised problem. On the other hand, for example, link prediction is a supervised problem, because you are trying to predict something, what is going to be the next product to be bought by someone. For example, if user A is going to buy a new product tomorrow, and what kind of product is going to be this product? So this is link prediction. We can do this by doing link prediction, and I think this is, of course, a supervised learning problem. So you can also assign the tasks in network mining to the basic tasks or the basic algorithm structure in terms of overall types of algorithms of data mining. So the supervised and the unsupervised. I don't know if I have answered your question.
Thank you very much. Any other question? If there's any other question, you can ask. Otherwise, anybody who would like to give verbal feedback, please, you're welcome. Yes, Dr. Virk, you would like to?
Yes, I will be very brief because there will be many people. First of all, I want to thank you, your PISTAR team, and especially you as the leader who have organized such an excellent workshop and 3 presentation by Dr. Pedro, who is really expert in his field. And
Thank
I
you
have
very much
really
for
enjoyed.
your words.
And there are new things which I never knew them before. Maybe my other colleagues, partners of this team might have known it, but I, as a geneticist, I didn't know many things. And many things you have told, they are really very useful in the real world. Even I can use them in many places. And in the workshop 1, you have very nicely told us about data presentation and how different variables and visualization of the data, and the 2 variables also you took up. Then modeling and evaluation was very interesting. I like that aspect where you did clustering and trees making. That's very useful information. Even in my sense, we can use it, and I have in fact used it myself. After your lecture, I had some data on some experiments which were field experiments, of course, in plant breeding, and we used different pollination bags and saw their effect on hybrid seed production. And different treatments. I did the cluster analysis, and what I predicted that some of the new bags, old bags, fabrics bags, and all those bags, they will fall into certain clusters. And actually they did. And I had 2 very beautiful clustering examples which I made. And that's a direct usefulness from your teaching, which I learned from you. So I think it can be used in many places. Even we can classify the germplasm, which we use as resources in plant breeding, different varieties, different old varieties, new varieties, some sort of accessions. We can group them together in clusters. And then within the cluster, we can work, and between clusters, we can work. And then we can find out how we can cross them to produce new things between different clusters and choose them. So in summary, there are many applications. And today you have shown another thing, which is a network mining. And that's, I find it very fascinating. And this is the real world today. It has such a usefulness in the real world in various fields. It's not confined to any one field. I was thinking of my own field, how I can apply it. And I was thinking, yeah, it can be applied. For example, we supply seed of different varieties to group of farmers or individual farmers over certain area. Say we give them 200 small kits, and then we follow the seed spread from each farmer, whom they have given, how much they have given, whether they have given within the village, within between the villages, how much distance, or across districts. We can map it in this using this data, this plan which you have shown today. We can make those figures and find out which are the center people and where it spreads and how it spreads, all those things. It's really fascinating. I like it. Thank you very much for this. This is a new field. I think it's a whole field, and probably Dr. Salaha maybe thinking of some students who can work on data mining for their MSc or PhD, and some of the topics which are really very interesting to me. And thanks a lot. And your presentation has been very, very nicely made, nice presentation, and the way you speak is very clear, and you speak very with a rhythm on a speed which is very comprehensible and one can understand, and you are open to questions also. I've been interrupting you many times, because of my poor knowledge, but you have been very kind to take those questions very kindly. And from other colleagues of my team, they have been also asking you questions, like Muhammad Abdus Salam has been saying so many things. So thanks a lot for your 3 presentations. Very interesting, brilliant presentations. I like them, and I hope everybody else have liked them. And there are new things which I have told. I appreciate. Thank you very much. And thank you very much for the PISTAR team, especially the leader who has organized this. workshop. Thank you.
It's the whole team, Dr. Vivek. Thank you very much. I have to now stop this feedback session, but please, ladies and gentlemen, do write in the chat, as some people are already doing. It is now my pleasure to invite my core team member, Dr. Haris Khurram, to say a few words in a more formal manner on behalf of PISTAR, words of appreciation for Dr. Pedro Campos. Over to you, Dr. Haris.
Thank you so much, Dr. Saleha. So,
Dr. Haris, can you open your camera?
right now, I think, sorry for that, I cannot do that. I feel some problem. So, so Honorable Professor Dr. Saleha Nagmi Habibullah, convener of the workshop, respected member of PISTAR team, valued guest, ladies and gentlemen. It is my privilege to have been asked to propose a vote of thanks and acknowledge the contribution of those who have contributed and worked to make this a successful workshop. I, Dr. Haris Khurram, on the behalf of PISTAR and entire team, first of all, thanks to Allah for making this series of workshop a grand success. I would like to express my gratitude to Dr. Pedro Campos, the keynote speaker, for giving an excellent coverage to the topic data mining. Thank you for your efforts. We all are inspired and learned a lot from your great words. Moreover, I would like to take this opportunity to record my thanks for Honorable Professor Dr. Saleha Nagmi Habibullah, convener of the workshop, Dr. Wasim Abbas, and the dynamic PISTAR team for arranging such an excellent learning opportunity for all of us. Well, ladies and gentlemen, such an event cannot happen overnight. Finally, I would like to thank everyone for their participation and being with us in this series. This is a great pleasure. Thank you very much.
Oh, okay. Thank you very much, Haris. That's very kind. I would like to share my screen one more time, if I may. If I can remember how to do that. Okay. I think you will be able to see my screen. Now, are you seeing my screen? Are you able to see my screen?
Yes.
Yes, we can.
Okay. So these were the words of appreciation given by Dr. Haris Khurram. And all I now want to say is that this beautiful series is now over. Hopefully we will have Dr. Pedro doing other things for us, and we will, we will not lose touch with him, but in fact, now he's also the country coordinator. But we will see all of you, or most of you, I hope, again at this upcoming conference, the conference and the post-conference workshop, which is on the 12th and 13th of March, not too many days away. The last thing is the group photograph, after which I would like to thank every single one of you, and we'll say goodbye. So please, this is it. Can you all open your cameras so that you can have a group photograph at the end? This is the new way of having group photographs. I do want to once more time thank my team, everybody, and for example, I can now see who I did not see in the beginning, Mr. Muhammad Iftikhar from my own core team, and also Dr. Sharka Hashmi is here, Ms. Kamal Aslam, Dr. Wasim, you also are having a problem with the camera today. Dr. Imran Anwar Ujjan, thank you very much. So I think Ms. Baliga is now going to open her camera. Okay, thank you very much. Thank you. And Pedro, would you like to say anything at the end? What you should give us some feedback. What was it for you, like for you?
I just replied, with very few words by saying that it was a pleasure to be here during these 3 workshops. I have to confess that in the beginning, I didn't know exactly how it was going to be, because, you know, we are doing this remotely. So we don't have you in front of me, and some of you are also teachers, maybe all of you are teachers, and you know that when you are a professor, we know to look at other people's faces to see if they are corresponding or agreeing with you or not agreeing, or, you know, so the body language is very important when we are teaching. And what I realized at the end of this series of workshops is that we didn't need indeed to be face-to-face, because these remote sessions worked very well. You were very active, interrupting whenever it was necessary to interrupt, which is something very important, because sometimes when I'm looking at the slides, I cannot see you, so I don't even know what if you are paying attention or if you are liking to you know or following the explanation. So of course I feel sometimes it's very difficult, but as I said, it was not a problem, because your feedback was excellent. So thank you for that. It was a pleasure. Because of that, it was a pleasure to prepare this third workshop of today. It was a little bit easier because I knew already what kind of feedback I could have, so I could prepare it in advance. And the only thing I can say now is that my contacts are available in case that you want to ask me anything else, or maybe start some kind of collaboration, in case if you want to have data that you can have my help to, I don't know, like do something with the data or give you some kind of advice. If it is of my expertise, I will be happy to do that. So thank you all for that.
Oh, thank you very much for that. We are above the time, but I still want to spend maybe 1 more minute. And Dr. Joyce, I can see you too. I thank you for being here. I want to say, Pedro, that we have also started international research projects. 2 projects are, I mean, small projects, but at least we have started. So like in one, we have Dr. Joyce and Dr. Awe from Nigeria, but now he's in Brazil, and also Dr. Raza. One is Ali Raza, he's in the other project, who is attending. But then there's Dr. Raza, who is in this project in which Dr. Awe and Dr. Joyce is, and also 4 of us from Pakistan. And the other one in which Ali Raza is there and Dr. Thomas is there. There we have 3 or 4 of us from Pakistan, and these 2 people from other countries. So actually this thing about being able to connect through Zoom or any other such medium, it has its own excitement. You know, you're sitting in your own home and you're able to connect with everybody. And we have spent weeks upon weeks trying to, to do this research work, these 2 different projects, one in the area of machine learning and the other in the area of statistical process control. So as you said, that if you could help in anything, I would like to say it now that I will invite everybody who is attending, that if you think you would like to get involved in some projects, research projects from the forum of PISTAR, and Dr. Pedro, if you could be the guide, maybe the leading person in 1 or 2 of them, that is another area that we aspire to do, because PISTAR is the Park Institute for Statistical Training and Research. So the research part is also there very much. And that's an idea that has come to me after your saying that you could help with data or some projects, something like that. What do you think?
I wouldn't say that I could be the leader, because maybe the data is yours and the idea is yours, and my role maybe could be to help you to solve some specific problems. I don't know exactly what we intend by a project, because sometimes, for example, in my country, when we say a project, the project is some kind of funds. So we need to be formal to this project, but the projects can also be informal. I mean, you can just meet another person and say, okay, let's do this together. Let's, I don't know, write a paper together. We have data, we can write. So that's this kind of things that I'm thinking about. So I can help from the side of my knowledge, and will help you as much as I can, of course, in the limits of our availability, of course. But you can count on me, of course.
Okay.
If you have any ideas, just share, and we will see how to manage this.
Thank you so much. Thank you so much. Okay, that's great. Okay, ladies and gentlemen, this is it. I thank you for your staying extra time also. And so therefore now I say goodbye and Allah Hafiz.